Okay. All right, I believe I am live right now. Unfortunately, this software for streaming things live has been having quite a few difficulties, and sometimes it's not working quite properly. So hopefully I can get that resolved when we're going on in the future. But let me just recap what happened in the morning. As I mentioned, I'm starting a new project, doing basically like I was doing the MIT challenge, doing MIT classes to learn quantum mechanics. I wrote a post on my website explaining kind of why I'm doing this, how I'm doing it, all those details. So I won't say that each time I'm doing the stream here. I'll just refer you to that post if you want to read and find out about what my motivations are. As for this, what did we do last in this morning when we had about 3 hours? Well, I went through the problem sets first to try to get a sense of what I already know, what I don't know, what I need to pay attention to when we're doing the lectures. And it was pretty good. I think that there's going to be maybe some issues because I'm missing 803. So particularly in the first problem set, it feels like it leans on 803, and I might have to do a little bit of backtracking to learn some of that material. We got through about 3.5, 4 problem sets. The last problem set, I didn't go through every single fine point because a lot of the math was over my head. So clearly we're going to have to learn something before we can do those problem sets. And then we turn to watching the first lecture. So I'm going to continue that, and I'm going to try to watch through as many of the lectures as I can today. And I'm hoping that by Wednesday-ish, we'll be finished up to about lecture 10. Then we can switch gears, focus on the problem sets, implement the stuff that we've learned. So I'm going to just switch right now to the screen showing the video, and we will continue to play. I will be playing it here, as I mentioned before. Sometimes me watching the video on the stream quality is not perfect. So if you want to watch it, obviously these videos are available. They're Creative Commons. That's how I'm streaming them now on MIT's website. So you can access all that information there. All right. So I also know that my notes are not entirely visible here. I'm at a little bit of a trade-off. I've kind of decided to make more of the screen visible, but my notes aren't perfectly readable. I'm hoping I can just give you a sense of how much notes I'm taking and what kinds of things I'm writing down. But I'm hoping at the end of this, I will scan everything so that I will have the notes as well available. So let's go back to this lecture. This was lecture 1 with Alan Adams, the professor.
It's just a weird thing about electrons. It's not a weird thing about the rest of the world. The rest of the world is completely reasonable. And no, that's absolutely wrong. Every object in the world has the same properties. If you take buckyballs and you send them through the analogous experiment, I will show you the data. I will show you the data when you take buckyballs and run through some experiment. You get the same effect. Now, buckyballs are huge, right? 60 carbon atoms. But okay, at that point you're like, dude, come on, huge, 60 carbon atoms. So there's a pendulum, depending on how you define building, in this building. A pendulum, which is used in principle, which is used to improve detectors to detect gravitational waves. There's a pendulum with I think it's 20 kilo mirror. Okay. And that pendulum exhibits the same sort of effects here. Okay. We can see these quantum mechanical effects in those mirrors. And this is breathtakingly awesome experiments done by Andrea Smallvalova, whose name I can never pronounce, but who's totally awesome. She's an amazing physicist. And you can get these kind of quantum effects of a 20 kilo mirror. So before you say something silly like, it's just electrons, it's 20 kilo mirrors. And if I could put you on a pendulum that accurate, it would be you. Okay? These are properties of everything around you. The miracle is not that electrons behave oddly. The miracle is that when you take 10 to the 27 electrons, they behave like cheese. That's the miracle. Okay? This is the underlying correct thing. Okay, so this is so far so good. Well, let's go deeper. Let's push it. And to push it, I want to design for you a slightly more elaborate apparatus. Slightly more elaborate experimental apparatus. And for this, I want you to consider the following device. I need to introduce a couple of new features for you. Here's a hard disk box. And it has an input. And the hard disk box has a hard temperature, and it has a soft temperature. And now in addition to this hard disk box, I'm going to introduce 2 elements. First, mirrors. Okay. And what these mirrors do is they take the incident electrons and nothing else, they change the direction of motion. Okay. Change the direction of motion. And here's what we mean by doing nothing else. If I take one of these mirrors, and I take, for example, a color box, and I take the white electrons that come out, and I bounce it off the mirror, okay, and then I send these into a color box, then they come out white 100% of the time. It does not change the observable color. All it does is change direction. Similarly with the hardness box, it doesn't change the hardness, it just changes the direction of motion. Okay, and every experiment we've ever done on these guys changes in no way whatsoever the color or the hardness by subsequent measurements. Cool? Just changes the direction of motion. And then I'm going to add another mirror. It's actually a slightly fancy set of mirrors. But all they do is they join these beams together into a single beam. And again, this doesn't change the color. You send in a white electron, you get out, and you measure the white, the color. On the other side, you get a white electron. You send in a black electron from here, you measure the color, you get a black electron again out. Cool? So here's my apparatus. And I'm going to put this inside a big box. And I want to run some experiments with this apparatus. I'm going to call it basic design. Any questions before you design? This part's fun. Okay. The first one, what I want to do now is I want to run some simple experiments before we get to fancy stuff. And the simple experiments are just going to warm you up. Okay. They're going to prepare you to make some predictions and some calculations. And eventually we'd like to lead back to this guy. So the first experiment, I'm going to send in white electrons. Whoops. I'm going to send in white electrons. And I'm going to measure at the end, and in particular at the output, the hardness. Okay. So I'm going to send in white electrons. And I'm going to measure the hardness. So this is my apparatus. I'm going to measure the hardness at the output. What I mean by measure the hardness is I throw these electrons into a hardness box and see what comes out. Okay, so this is experiment 1. So let me draw this. I need to begin the diagram. We send white into, so the hardness box, mirror, mirror, mirrors. And now, oops, we're measuring the hardness out. And the question I want to ask is, how many electrons come out a hard aperture, and how many electrons come out the soft aperture of this final hardness box? Okay. So I'd like to know what fraction come out hard and what fraction come out soft. I send an initial white electron, for example, I took a color box and took the white output, send it into the hardness box, mirror, mirror, hard, hard, soft. And what fraction come out hard, and what fraction come out soft? Okay, so just think about it for a minute. Okay. And when you have a prediction in your head, raise your hand.
So I'm going to guess, well, based on everything that's been discussed so far, I'm going to guess it's 50-50. Let's see if that's true.
Okay, walk me through your prediction. 50-50. How come? Good. Awesome. So let me say that again. So we've done the experiment. You send a white electron in the hardness box. We know that it's non-predicted. 50-50. So if you take a white electron and you send it into the hardness box, 50% of the time will come out the hard aperture, and 50% of the time will come out the soft aperture. Now, if you take the one that comes out the hard aperture, then you send it up here, send it up here. We know that these mirrors do nothing to the electron, to the hardness of the electron, except change the direction of motion. We've already done that experiment. So what do you measure the hardness at the end? What do you get? Hard, because it came out hard, mirror, mirror, hardness, hard. But it only came out hard 50% of the time because we sent in initially white electron. Yeah. What about the other 50%? Well, the other 50% of the time it comes out soft aperture and follows what they call the soft path to the mirror, mirror, hardness. And it was soft, mirror, mirror, hardness, you know it comes out soft. 50% of the time comes out this way, and then it will come out hard. 50% follows the soft path, and then it will come out soft. Was this the logic? Good.
Mm-hmm.
How many people agree with this?
I agree with that.
Solid. How many people disagree? No abstention. Okay. So here's the prediction. Surveys. Oh, yep.
Question. Could you justify that prediction without talking about, oh, well, half the electrons were initially electrically hard and half were initially electrically soft? By just saying, well, we have a hardness box, and then you join these electrons together again, so we don't know anything.
Well, that's
it. So just like sending white electrons into one hardness box instead of two.
Yeah, that's a really tempting argument, isn't it? So let's see. We're going to see in a few minutes whether that kind of argument is reliable. But so far we've been given 2 different arguments that lead to the same prediction, 50-50. Yeah. Question.
The electrons need to activate themselves. Like when you get them together.
Yeah. This is a very good question. So here's the question. Look, you're sending a bunch of electrons into this apparatus, but if I take 2, look, I can take 2. You know, take 2 electrons, you put them close to each other. What do they do? Right? They interact with each other through a potential. Right? So yeah, we're being a little bold here, throwing a bunch of electrons in. It's like, oh, they're independent. So I'm going to do one better. I will send them in one at a time. 1 electron through the apparatus, and then we'll wait for 6 weeks. And then I'll say, gee, you guys laugh, you think that's funny, but there's a famous story of a guy who did a similar experiment with photons. A French guy, and French, they know what they're doing. So he wanted to do it the same experiment with photons, but the problem is if you take a laser and you shine it into your apparatus, then there are like 10 to the 18 electrons in there, or photons in there, and the photons, who knows what they're doing with each other, right? So I want to send in one photon. The problem is it's very hard to get a single photon. Very hard. So what he did, figured out, he took an opaque barrier. I don't remember what it was. It was some sort of film on top of glass. I think it was some sort of oil par film. Or do you remember what he used? Okay, so he takes a film and it has this opaque property that such that the photons that are emitted upon it get absorbed. Once in a blue moon, a photon manages to make its way through. Literally, like once every couple of days. Okay, now or a couple of hours, I think. So it's going to take a long time to get any sort of statistics. But he has this advantage that once every couple of hours or whatever, a photon makes its way through. That means inside the apparatus, it takes a picosecond to cross. Triumph, right? That's what we was talking about. So he does this experiment, but as you can tell, you start the experiment, you press go, and then you wait for 6 months. Side note on this guy, liked boats, really liked yachts. So he had 6 months to wait before doing the beautiful experiment, having the results. So what did he do? Went on a world tour in his yacht, comes back, collects the data, and declares victory because indeed he saw the effect he wanted. So I was not kidding. we really do it. So I will take your challenge and single electron, throw it in. Let it go through the apparatus, takes mere moments, wait for a week, send in another electron. No electrons are interacting with each other. Okay? Just a single electron at a time going through this apparatus. Other complaints? Sorry? Oh, you'll get that. I have a hard time resisting. So here's a prediction. 50-50. We now have two arguments for this. So again, let's vote after the second argument. 50-50, how many people? You sure? Awesome. Okay, how many people don't think so? Very small dust. Okay, it's correct. Yay! Okay. So I like messing with you guys. So remember, we're going to go through a few experiments first, where it's going to be very easy to predict the results. We've got 4 experiments like this to do, and then we'll go on to the interesting example. But we need to go through them so we know what happens, so we can make an empirical argument rather than a principal argument. So there's the first experiment. Now I want to run the second experiment. And the second experiment, same as the first, a little bit louder, a little bit worse. The second experiment, we're going to send in hard electrons, and we're going to measure color. Okay, so again, let's look at the apparatus. We send in hard electrons, and our apparatus is hardest box. Are they hard and a soft aperture? And now we're going to measure the color at the output. Color. What if I did a big one? And now I want to know what fraction come out black and what fraction come out white. We're using lots of monkeys in this process. Okay, so this is not rocket science. Rocket science isn't that complicated. Neuroscience is much harder. This is not neuroscience. Okay, so let's figure out what this is. Predictions. So.
All right, what do I predict? Well, the hardness box is going through. How much is black and white? I'm gonna guess it's 50-50 because we didn't ever measure the color before.
And think about your prediction in your head. Come to a conclusion. Raise your hand when you have an idea. Just because you don't raise your hand doesn't mean I won't call on you. 50-50 black and white. I like it. Tell me why. Great. So the statement, I'm going to say that slightly more slowly. That was exactly that was an excellent argument. We have a hard electron. We know that hardness boxes are persistent. If you send a hard electron in, it comes out hard. So every electron incident upon our apparatus will transit across the hard trajectory. Right? It will bounce, but it is still hard because we've already done that experiment. We already do nothing to hardness. So we send a hard electron into the color box, and what comes out? Well, we've done that experiment too. Hard into color, 50-50. So the prediction is 50-50. This is your prediction. Is that correct? Awesome. Okay. Let us vote. How many people think this is correct? Gusto, I like it. How many people think it's not? All right. Yay! This is correct. Okay. Third experiment, slightly more complicated. But we have to go through these to get to the good stuff. So humor me for a moment. Third, let's send in white electrons, and then measure the color at the output port. So now we send in white electrons, same beast, and our apparatus is hardness box with a hard path and a soft path. Mirror, box. Join together into our out, and now we send those out electrons into a color box.
Ooh.
And our color box, black. And now the question is, how many come out black and how many come out white?
All right. I feel like the answer is going to be 100% white, but I'm thinking that just because this seems like a trick question. So I'm gonna go with what my naive understanding is, because that's. I'm going to say 50-50 because this is sort of what we've been led to believe so far.
Okay.
What is the answer?
Think through logic, follow the electrons, come up with a prediction, raise your hand when you have a prediction. right, so let me say that again out loud and tell me if this is an accurate sort of extension of what you said. I'm just going to use more words, but it's, I think, the same logic. We have a white electron, initially white electron. We send it into a hardness box. When we send a white electron into a hardness box, we know what happens. 50% of the time it comes up hard, the hard aperture. 50% of the time it comes out soft aperture. Consider those electrons that came out hard aperture. Those electrons that came out the hard aperture will then transit across the system, preserving their hardness by virtue of the fact that these mirrors preserve hardness, and end up in a color box. When they end in the color box, when that electron, the single electron in the system, ends in this color box, then we know that a hard electron entering color box comes out black or white 50% of the time. We've done that experiment too. So for those 50% that came out hard, we get 50-50. Now consider the other 50%. The other half of the time, a single electron in the system will come out the hard, this will come out soft aperture. It will then proceed along the soft trajectory, bounce, not changing its hardness, and is then a soft electron incident on the color box. But we've also done that experiment, and we get 50-50 out black and white. So those electrons that came out hard come out 50-50, and the electrons that come out soft come out 50-50. And the logic then leads to 50-50 twice, 50-50. Was that an accurate statement? Good, it's a pretty reasonable extension. Okay, let's vote. How many people agree with this one? Okay, how many people disagree? Yeah, okay, so vast majority agree, and the answer is no, this is wrong. In fact, of these, 100% come out white, and 0 come out black. Never, ever does an electron come out black aperture.
What? It's crazy.
I'd like to quote what a student just said, because it's actually the next line in my notes, which is, what the hell is going on? So let's run a series of follow-up experiments to tease out what's going on here. Okay, so something very strange. Let's just all agree, something very strange just happened. Okay, we sent a single electron in, and that single electron comes out the hardest box. Well, it either came out the hardest box or came out the softness. It either came out the hard aperture or the soft aperture. And if it came out the hard, we know what happens. If it came out soft, we know what happens. And it's not 50-50, right? So we need to improve the situation. So, well, okay, go ahead. Yeah.
So for the second hardest box, are we collecting some of the soft partially?
The second, you mean the first hardest box?
Or the one,
Which one? Sorry. This guy? Oh, that's a mirror, not a hardest box. All this stuff. Oh, thanks for asking. Okay, yeah, sorry. I wish I had better notation for this, but I don't. There's a classic. Well, I'm not going to go into it. So, remember that thing where I can't stop myself from telling the story. So all this does is just a set of mirrors. It's a set of fancy mirrors, and all it does is it takes an electron coming this way and an electron coming this way, and both of them get sent out the same direction. It's like a beam doing, right? It's like a Y junction. That's all it is. So if you will, imagine the box is a box, and you take, I don't know, Professor Sweetbox, and you put it inside, and every time an electron comes out this way, he throws it out that way. Every time it comes in this way, he throws it out that way. But he'd be really ticked at you for putting it in a box, but he did the job well. Yeah. This works if you go 1 electron at a time. This works if you go 14 electrons at a time. It works. It works reliably. Yeah. Yeah, I know. Right? Yeah. So the question was, what's the difference between this experiment and the last one? Yeah, good question. So we're gonna have to answer that. Yeah. Apparently, it's a lot like when we're measuring, right? Because we send in the white electron, and at the end, we get out that it's still white. So somehow this is like not doing anything. But how does that work? So that's an excellent observation, and I'm going to build you now a couple of experiments that tease out what's going on. And you're not going to collect the answer. Yeah.
The white electrons are generated this way.
The white electrons were generated in the following way. I take a random source of electrons, I rub a cat against a balloon, and I sharpen the balloon. Okay. And so I take those random electrons, and I send them into a color box. We have previously observed that if you take random electrons and throw them into a color box, and pull out the electrons that come out the white aperture, if you then send them into a color box again, they're still white. So that's how I generated them. I could have done it by rubbing the cat against glass, or rubbing it against, me, right? Just stroke the cat. Any randomly selected set of electrons sent into a color box, and then from which you take the white electrons. Yeah, exactly. Yeah. That's a really good question. So I don't want to hear something I'm going to be very careful not to say in this class to the degree possible. I'm not going to use the word to know. Good. Measure is a very slippery word too. I've used it here because I couldn't really get away with not using it. But we'll talk about that in some detail later on in the course. For the moment, I want to emphasize that it's tempting but dangerous at this point to talk about whether you know or don't know, or whether someone knows or doesn't know. For example, the monkey inside knows or doesn't know, right? So let's try to avoid that and focus on just operational questions of what are the things that go in, what are the things that come out, and what probabilities. And the reason that's so useful is that it's something that you can just do. Right? There's no ambiguity about whether you've caught a white electron in a particular spot. Now, in particular, the reason these boxes are such a powerful tool is that you don't measure the electron, you measure the position of the electron. You get hit by the electron or you don't. And by using these boxes, we can infer from their position the color or the hardness. Okay, and that's the reason these boxes are so useful. So we're inferring from the position, which is easy to measure. You get beamed or you don't. We're inferring the property that we're interested in. So it's a really good question. Keep it in the back of your mind, and we'll talk about it on and off the rest of the semester. Yeah.
So when do you have a set of these anyway right here?
Perfect question. Okay, this leads me into the next experiment. So here's the modification that, thank you, that's a great question. Here's the modification of this experiment. So let's rig up a small, hold on, I want to go through the next series of experiments and I'll come back to questions, and these are great questions. So I want to rig up a small movable wall, okay, a small movable barrier, and here's what this movable barrier will do. if I put the barrier in, so this would be in the soft path. When I put the barrier in the soft path, it absorbs all electrons incident upon it and impedes them from proceeding. Okay, so you put a barrier in here, put a barrier in the soft path, no electrons continue through. An electron incident cannot continue through. Okay. When I say that the barrier is out, what I mean is it's not in the way. I've moved it out of the way. Cool? So I want to run the same experiment. And I want to run this experiment in the following way. I want to run the experiment using the barriers to tease out how the electrons transit through our apparatus. Okay. So, experiment 4. Let's send in a white electron again. I'm going to do the same experiment we just did and color at out. But now with a wall in the south path. Wall in soft. Okay? So that's this experiment. So we send in white electrons and we send out. And at the output we measure the color. Okay, as before. And the question is, what fraction come out? What fraction come out? Black, and what fraction come out? White. Okay. So again, everyone think through it for a second. Just take a second. And this one's a little sneaky, so just feel free to discuss with the person sitting next to you.
50-50. I'm going to guess 50-50.
All right, now that everyone's had a quick second to think through this one, let me just talk through what I expect from the point of these experiments, and then we'll talk about whether this is reasonable. So the first thing I expect is that, look, if I send in a white electron and I put it in a orange path, I know that 50% of the time goes out hard, 50% of the time goes out soft. If it goes out the soft aperture, it's going to get eaten by the barrier, right? It's going to get eaten by the barrier. So first thing I predict is that the output should be down by 50%. However, here's an important bit of physics, and this comes to the idea of locality. I didn't tell you this, but these arm lengths in the experiment I did, 3,000 kilometers long. 3,000 kilometers. That's too long here. 10 million kilometers long. Really long. Very long. Now imagine an electron that enters this. So initially white electron. If we had the barriers out, right? If the barrier was out, what would we get? 100% white, right? We just did this experiment to our surprise. So if we did this, we got 100%. That means an electron, any electron going along the south path comes out white. Any electron going along the hard path goes out white. They all come out white. So now if I imagine I do this, imagine we put a barrier in here, 2 million miles away from this path. How does a hard electron along this path know that I put the barrier there? I'm going to make it even more sneaky for you. I'm going to insert the barrier along the path after I launch the electron into the apparatus. Okay? And when I send in the electron, I will not know at that moment whether nor will the electron there, whether, because they're not very smart, whether the barrier is in place. And this is going to be millions of miles away from this guy. Okay? So an electron out here can't know. It hasn't been there. It just hasn't been there. It can't know. But we know that when we ran this apparatus without the barrier in there, it came out 100% white. But I can't possibly know whether the barrier is in there or not. Right? It's over here. So what this tells us is that we should expect the output to be down by 50%. But all the electrons that do make it through must come out white because they didn't know that there was a barrier there. It didn't go along that path. Yeah. Oh, I was just sorry. No, thank you. Thank you. That was a slip of the tongue. I was making fun of the electron. So, in that particular case, I was not referring to my or your knowledge. I was referring to the electron's tragically impoverished knowledge. Yeah. Well, here's the more troubling thing. Imagine it didn't come out 100% white. Then the electron would have demonstrably not gone along the soft path. It would have demonstrably gone through the hard path because that's the only path available to it. And yet it would still have known that millions of miles away there's a barrier on a path that didn't take. So which one's more upsetting to you? Okay. And personally, I find this one the less upsetting of the two. Okay. So the prediction has become our output should be down by 50% because half of them get eaten. But they show up in white because those that didn't get eaten can't possibly know that there was a barrier here. Millions of miles away. Okay. So we run this experiment, and here's the experimental result. In fact, the experimental result is yes, the output is down by 50%, but no, not 100% white. 50% white.
What?
50% white. The barrier, if we put the barrier in the hardest path, if we put the barrier in the hardest path, still down by 50%, and it's at odds. 50-50. How did the electron go? I'm making fun of it. Yeah.
Here's my question is,
before we asked how that was, there's lots of paths. No, before over there, there were two paths. Excellent. Exactly. So actually, this problem was there already in the experiment we did. All we've done here is tease out something that was existing in the experiment, something that was disturbing because of those mirrors and the option of taking two paths, but somehow changed the way that the electron behaved. How is that possible? And here we're seeing that very sharply. Thank you for that excellent observation. Yeah. Yeah, this is totally reasonable. So the question is basically, let's take this experiment and let's make it even more intricate by, for example, replacing these mirrors by color boxes. Okay, so here's the thing I want to emphasize. Something that, well, how to say it? I strongly encourage you to think through that example. And think through that example, come to my office hours and ask me about it. So that could be studying a different experiment. And different experiments are going to have different results. So we're going to have to deal with that on a case-by-case basis. It's an interesting example, so it takes a bit far from where we are right now. But after we get the punchline from this, come to my office hours and ask me exactly that question. Okay? Yeah. Yeah. How do we know the boxes work? Well, these are the same boxes we used from the thing. We tested them over and over. Well, how to say? There's no other way to build a box that does the properties that we want, which is like setting color and it comes out color again, and the mirrors behave this way. There's any box that does those first set of things, which is what I would call a color box, does this too. There's no other way to do it. I mean, I don't mean this because Oh, sure, you can. You take the electron that came out of the color box. That's what you mean by saying it's white. Well, but that's what it means to say the electron is white, right? It's like how do you know the meaning out? You say, oh, I know what, right? But you imagine like, look, that's not a test of whether I'm out. Well, what is a test of whether that's how you test? What's your name? I'm out. Oh, great. So that's what I mean by white. Now you might quibble that that's a stupid thing to call an electron, and I grant you that. But it is nonetheless a property that I cannot carefully engage. Okay, so I've been told that I never asked a question from the table already. Yeah. No. This experiment has been done again by some French guys. There's the French look, dude. So there's this guy on this day. Great experimentalist, great physicist, and he's like lots of beautiful experiments on this topic. And send me an email, I'll post some example papers and reviews by him, and he's a great writer on the page, so just send me an email. Okay, so we're lowish on time, so let me move on. So what I want to do now is I want to take the lesson of this experiment and the observation that was made a minute ago, that in fact the same problem was present when we ran this experiment about 100%, we should have been freaked out already. And I want to think through what that's telling us about the electron, the single electron, as it transits the apparatus. The thing is, at this point, we're in real trouble. And here's the reason. Consider a single electron inside the apparatus. And I want to think about the electron inside the apparatus while all walls are out. So it's this experiment. Consider the single electron. We know with total confidence, with complete reliability, that every electron will exit this color box out the white aperture. We've done this experiment. We know it will come out white. Yes? Here's my question. Which word did it take? Not a spoiler. Which word did it take? I'm asking the question. That's why you care. I'm a professor here. Come on. Which word did it take? Okay, let's think through the possibilities. Grapple with this question in your belly. Let's think through the possibilities. First off, did it take the hardest path? So as it transits through the single electron transiting through this apparatus, did it take the hard path, or did it take the soft? These are millions of miles long, millions of miles apart. This is another, ridiculous question. Did it go that millions of miles left or millions of miles that direction? Did it take the hardest path? Ladies and gentlemen, did it take the hardest path, the hard path? Well, we ran this experiment by putting a wall in the soft path. And if we put a wall in the soft path, then we know it took the hard path because no other electrons come out of those the hard path, right? On the other hand, if it went through the hard path, it would come out 50% of the time white, 50% of the time black. But in fact, in this apparatus, it comes out always 100% white. It cannot have taken the hard path. No. Did it take the soft path? Same argument, different sign, right? No. Well, this is not looking good. Well, look, maybe this was suggested. Maybe it took both. Maybe electrons are sneaky little devils that split in two, and part goes one way, part goes the other. Maybe it took both paths. So this is easy. We can test this one. Here's how I'm going to test this one. Sorry. Actually, we're going to do that again. So we can test this one. So if you took both paths, here's what you should be able to do. You should be able to put a detector along each path, and you'd be able to get half an electron on one side and half an electron on the other. Or maybe two electrons, one on each side, one on the other. Right? So this is the thing that you predicted. You said it went both. So here's what we'll do. We will take detectors, we will put one along the hard path and one along the soft path. We will run the experiment, and then observe whether and ask whether we see two electrons, we see half and half, or we see. And the answer is you always see one electron on one of the paths. You never see half an electron. You never see a squishy electron. You see one electron on one path, period. It did not take both. You never see an electron split in two, divided, confused. No. Well, it didn't take the hard path. It didn't take the soft path. It didn't take both. There's one option left. Neither. Well, I say neither, but what about neither? And that's easy. Let's put a barrier in both paths. And then what happens? Nothing comes out, right? So no. Okay. So now, to repeat repeat an earlier prescient remark from one of the students. What the hell? So here's the world we're facing. I want you to think about this. Take this seriously. Here's the world we're facing. And when I say here's the world we're facing, I don't mean just these experiments. I mean the world around you, 20-kilo mirrors, buckyballs. Here's what they do. When you send them through an apparatus like this, every single object that goes through this apparatus does not take the hard path. It does not take the soft path. It doesn't take both. And it does not take neither. And that pretty much exhausts the set of logical possibilities. So what are electrons doing when they're inside the apparatus? How do you describe that electron inside the apparatus? You can't say it's on one path, can't say it's on the other, it's on both, and it's not on either. What is it doing halfway through this experiment? So if our experiments are accurate, to the best of our ability to determine they are, and if our arguments are correct, and that's on me, then they're doing something. These electrons are doing something we've just never thought of before, something we've never dreamt of before, something for which we don't really have good words in the English language. Apparently, empirically, electrons have a way of moving. Electrons have a way of being, which is unlike anything that we're used to thinking about. And so do molecules, and so do bacteria, so does chalk. It's just harder to detect in those objects. So physicists have a name for this new mode of being, and we call it superposition. Okay. Now, at the moment, superposition is code for I have no idea what's going on. Okay. The usage of the word superposition would go something like this: an initially white electron inside this apparatus, with the walls out, is neither hard nor soft, nor both, nor neither. It is in fact in a superposition of being hard and of being soft. This is why we can't meaningfully say this electron is some color and some hardness. Not because our boxes are crude, and not because we're ignorant, though our boxes are crude, and we are ignorant. It's deeper. Having a definite color means not having a definite hardness, but rather being a superposition of being hard and being soft. Every electron every electron exits a hardness box, either hard or soft. But not every electron is hard or soft. It can also be a superposition of being hard or being soft. The probability that we subsequently measure it to be hard or soft depends on precisely what superposition it is. For example, we know that if an electron is in the superposition corresponding to being white, then there are even odds of it being subsequently measured to be hard or to be soft. So, to build a better definition of superposition, then I have no idea what's going on. Is going to require a new language, and that language is quantum mechanics. And the underpinnings of this language are the topic of the course. And developing a better understanding of this idea of superposition is what you have to do over the next 3 months. Now, if all this troubles your intuition, well, that shouldn't be too surprising. Your intuition was developed by throwing spears and, running from tigers and catching toast that jumps out of the toaster, right? All of which involves things so big and with so much energy that quantum effects are negligible. As a friend of mine likes to say, you don't need to know quantum mechanics to make chicken soup. However, when we work in very different regimes, when we work with atoms, when we work with molecules, when we work with in a regime of very low energies and very small objects, your intuition is just not a reasonable guide. It's not that the electrons, I cannot emphasize this strongly enough, it is not that the electrons are weird. The electrons do what electrons do. This is what they do, and it violates your intuition, but it's true. The thing that's surprising is that lots of electrons behave like this. Lots of electrons behave like cheese and chalk. And that's the goal of 804. To step beyond your daily experience and your familiar intuition, and to develop an intuition for this idea of superposition. And we'll start in the next lecture. We'll see you on Thursday.
Okay, wow, good intro class. This is. I'm just gonna check in on the chat. I think there's some people coming in here. So first of all, I'll just switch over here because we're now finished the first lecture. So I'm going to just close my book real quick and just kind of recap what was said in the lecture. This is actually a pretty helpful tool for helping your understanding after you've been in a lecture, is just to put all your notes away. Don't read them, because if you read them, then that kind of defeats the purpose. Put your notes away and just sort of ask yourself, what did I just see? Now, I know it's a little hard for you if you've been watching this because maybe stream quality wasn't as good as it was for me watching it. I was watching at 1.5 times the speed. Maybe that was a little too fast for you, especially if English isn't your first language. It might be a little bit harder to understand at that speed. And 3, I started half of the lecture in the morning, so I kind of went in about halfway. So this, just apply this idea in abstract and maybe not to the lecture we just watched. So basically, what was discussed in this thing? Well, I think the idea was that the professor wanted to show how strange this thing that we're dealing with is. That we need a new intuition about subatomic particles, things like electrons, photons. And he's pointing out that this isn't just some kind of triviality that applies to only very microscopic things. That this is the basic way that the universe works. And that the surprising thing, the thing that we need to come around like full circle on, is to find that things don't behave that way when they're large objects, or they don't seem to behave that way when they're large objects, is the surprising thing. So to do so, he gave kind of a sort of a high level summary where he described two properties of electrons: hardness and color. So the hardness was either hard or soft, and the color was either black or white. And he had what he called hardness boxes and softness, or hardness boxes and color boxes. And the hardness box was some kind of black box. He's saying that it doesn't matter how you construct it; they've constructed it many different ways. So we're just sort of take him at his word for that. But that you put it in, and there's sort of two different output paths, and one of them, if you send in electrons, it will be in the hard path, and one of them will be in the soft path. And if you put two hardness boxes next to each other, they will preserve that property. So electrons that go through the hardness path and are found to be hard will be hard when you put them through another hardness box. And that's sort of empirically how we observe this property of hardness. Same thing with the color box. And the first surprising thing is that if you put a color box in between two hardness boxes, it resets the properties of the electrons. So electrons that were first hard, and then you figure out whether they're black and white, then you go through again, and if you take, let's say, all the hard electrons, put them through an apparatus, you take all the white electrons from that, you don't get all hard electrons again, you get a 50-50 mix, which is itself surprising because normally properties are consistent. If you have, let's say, a baseball that's hard and black, and it goes through a tube, you don't expect it to suddenly turn soft later because it was hard in the beginning, right? So that's the first thing that's surprising. The second thing is he describes sort of an apparatus where you take it through the hardness box, you split it, so you split those beams, and you reflect them, and you merge the beams back again. And this could be a huge, huge device, in theory, as large as possible. And the second surprising thing is that when you take these electrons and they go through this box, and it goes through the beam splitter and then the beam joiner, that same principle of having gone through the hardness box doesn't apply anymore. So even though we sent it through the hardness box, all the white electrons come out white on the other end, all the black electrons end up black on the other end. They don't have this resetting property, which is also surprising because it's kind of, well, what happened in the middle? And so he's talking about how if we put a barrier, for instance, and we block one of them, and again, we put this barrier, and we could even put the barrier in the middle of the thing so that the electron doesn't even know that, in theory, that there's no way for it to know it was, millions of miles away. It was would have to, know instantaneously over very vast distances that it was blocked on that end, and it doesn't. But yet it still seems to be preserved in that way. So I don't think that there's anything really quantitative right now about this process. We've just done the first lecture. The whole idea is just to kind of illustrate the puzzle. So I want to move forward. I think this is a very important lecture. I just really like this one. I did watch this one before, and I just think it's a great lecture just because of how he conveys how confusing this is. Like if I go through my notes, I'll open my notes now just so you can see here. But if I go to the here, he says, well, which route did the electron take if we are to consider that there's no barriers and we have this kind of weird apparatus? Well, did it take the hard path? Well, no, because we know that if it takes a hard path, it would preserve this relation where it gets reset. Did it take the soft path? Well, by the same argument, no. Did it take both paths? Well, no, because again, the same reason that we never see more than one electron. And did it take neither paths? Well, no, because we see one on the other side. So his argument is that there's this new concept, superposition, which had to be developed to deal with the fact that these four properties, A, B, A and B, or neither A or B, seem to be like the logically exhaustive options, and the answer is none of those. And so we had to create this new concept of superposition. So this is really exciting. This is just a fun class for warming up and getting excited about the course. I'm going to jump forward and go into lecture 2 now. And basically, I'm just going to focus on the lectures until I get to about lecture 10, and then I'm going to take a break and go back to problems. So you'll probably just see me writing notes like these ones and watching the class. I'm not going to be talking that much. I do kind of see a little bit of the chat, but I'm probably going to be ignoring it most of the class because otherwise it's just going to be distracting. But if you have any questions, you can send them in there, and I'll try to take little breaks after the lectures, and I can try to deal with them here. So let us open up the next class here. I'll see if I have to reset this screen. All right. Oh, okay. I'm going to expand this, and I should be able to. All right, lecture 2, experimental facts of life. Let me just write this down here. I think I'm still on 1.5 times speed. I'm going to use this as my default for right now. I like to go a little faster in the first version, as long as I'm not struggling to understand what he's saying. If I struggle to understand, especially when he starts doing math, that's probably going to be when I slow it down. But so far, I mean, I do have the advantage of having seen these before, although I probably watched them at 1.5 times the speed the first time too. So let's watch it here, and I might speed it up for the beginning part of the class just because there's some of that as well.
For Creative Commons license, your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so today's task is going to be to outline some of the basic experimental facts that we will both have to deal with and that our aim should be to understand and model through the rest of the course. Physics doesn't tell you some abstract truth about why the universe is the way it is. Physics gives you models to understand how things work and predict what will happen next. And what we will be aiming to do is develop models that give us an intuition for the phenomena and allow us to make predictions. And these are going to be the experimental facts that we'll have to both explain, develop an intuition for, and be able to predict consequences of. So we'll start off with, so let me just outline them. So first fact, atoms exist. I'll go over some of the arguments for that. Randomness, definitely present in the world. Atomic spectra are discrete and structured. We have a photoelectric effect, which I'll describe in some detail. Electrons do some funny things, in particular electron diffraction. And sixth and finally, Bell's inequality, something that we will come back to at the very end of the class, which I like to think of as sort of frame for these.
Atomic spectra. Sorry, this is what I often do if I want to make sure I copy down all the notes. I don't try to get everything when I'm doing notes. I have these lectures, so I can go back with it. But I do like to write these all down because they're going to be kind of topics to discuss. So when I'm looking back at the notes and I need to get it. All right, so this is probably going to be what's discussed in the class.
So, we'll see where this is going. So, everyone in here knows that atoms are made of electrons and nuclei. In particular, you know that electrons exist because you've seen a cathode ray tube. I used to be able to say you've seen a TV, but you all have flat math TV, so this is useless. So, a cathode ray tube is a gun that shoots electrons at a phosphorescent screen, and every time the electron hits the screen, it induces a little phosphorescent, little glow, and that's how you see on a CRT. And so, as was typically stated long ago by a very famous physicist, if you can spray them, they exist. It's a pretty good argument. There's a better argument for the existence of electrons, which is that we can actually see them individually. And this is one of the most famous images in high-energy physics. It's from an experiment called Gargamel, which was a 30 cubic meter tank of liquid freon pulsing just at its vapor pressure 60 times a second. And what this image is apart from all the schmutz, you're watching a trail of bubbles in this depressurizing freon that wants to create bubbles because the nuclei bubbles. What you're seeing there in that central line that goes up and then curls around is a single electron that was nailed by a neutrino incident from a beam at CERN, where currently the LHC is run. And this experiment revealed two things. First, to us, it will reveal that you can see individual electrons, and by studying the images of them moving through fluids and leaving a disturbing wake of bubbles behind them, we can study their properties in some considerable detail. The second thing it taught us is something new. We're not going to talk about in detail. Is that it's possible for a neutrino to hit an electron. And that process is called a weak neutral current for sort of stupid historical reasons. Actually, a really good name. And that was awesome and surprising. So this picture is both a monument to the technology of the experiment, but also to the physics of weak neutral currents and electrons. They exist if you can discover neutrinos by watching them. Okay. Secondly, nuclei. We know that nuclei exist because you can shoot alpha particles, which come from radioactive decay, at atoms, and you have your atom, which is some sort of big thing. I'm going to make the atom. I'm going to find out by making a sheet of atoms. Maybe a foil, very thin foil stuff. And then I'm going to shoot very high energy alpha particles incident to this. Probably everyone's heard of this experiment. It was done by Rutherford and Geiger and Marsden, in particular, his students at the time, postdocs, they're called. And you shoot these alpha particles in, and if you think of these guys as some sort of jelly-ish lump, then maybe they'll deflect a little bit, but if you shoot a bullet through jello, you're sort of, maybe it gets deflected a little bit of the jello. I mean, come on. And the thing that was shocking is you shoot these alpha particles in, and every once in a while, they bounce back at 180, 160 degrees. Rutherford likened this to rolling a bowling ball against a piece of paper and having it bounce back. Kind of surprising. And the explanation here that people eventually came up on is that atoms are mostly zero density, except they have very, very high density cores, which are many times smaller than the size of the atom, but where most of the mass is concentrated, and as a consequence, most of the inertia. And so we know that atoms have substructure, and the picture we have is that, well, if you scrape this pile in the middle, you can pull off the electrons, leaving behind nuclei, which have positive charge, because you scrape off the electrons that have negative charge. So we have a picture from these experiments that there are electrons, and there are nuclei, which I'll just write N as plus, which are the constituents of atoms. Now, this leads to a very natural picture of what an atom is. If you're a 19th century physicist, or even early 20th century physicist, it's very natural to say, well, if I know if I have a positive charge and I have a negative charge, then they attract each other with a 1 over R on this Q1, Q2, Q1, Q2 over R potential. This is just like gravity, right? The Earth and the Sun are attracted with an inverse R potential. This leads to Keplerian orbits. And so maybe an atom is just some sort of orbiting classical combination of an electron and nucleus, possibly German nucleus. The problem with this picture, as you explore in detail in your first problem on the problem set, is that it doesn't work. What happens when you accelerate a charge? It radiates. Yeah, exactly. So it's radiating. It's got to lose energy. It's dumping energy into this out of the system. So it's got to fall lower into the potential. Well, it falls lower. It speeds up. It radiates more because it's accelerating more to stay in a circular orbit. It radiates more. That means it has to fall further down. So on the problem set, you're going to calculate how long that takes. And it's not very long. And so the fact that we persist for more than a few picoseconds tells you that this is not a correct picture of an atom. Okay. So in classical mechanics, atoms could
Spoilers from problem set 1.
Atoms exist. So we have to explain that. That's going to be our first challenge. Now, interestingly, Geiger, who was this collaborator, Rutherford, junior collaborator Rutherford, went on to develop a really neat instrument. So suppose you want to see radiation. We do this all the time. I'm looking at you and I'm seeing radiation, seeing light. But I'm not seeing ultra high energy radiation. I'm seeing radiation in the electromagnetic waves in the optical spectrum. I'm also not seeing alpha particles. So what Geiger wanted was a way to detect, without using your eyes, radiation that's hard to see. So the way he did this is he took a capacitor and he filled the surrounding capacitor with some noble gas. It doesn't interact. It's very hard to ionize. And if you crank up the potential across this capacitor plate high enough, what do you get? A spark, right? You all know this. If you crank up the capacitor, eventually breaks down because the dielectric in between breaks down. You get spontaneous sparking. So what he figured was, look, if I take a capacitor plate and I charge it up, but not quite to break down, just so you have a good potential, and another charged particle comes along through, like an alpha particle, carries charge +2, that positive charge will disturb things and will add extra field effectively and lead to the nucleation of the spark. So the presence of a spark when this potential is not strong enough to induce a spark spontaneously indicates the passage of a charged particle.
Geiger counter.
Later with Marshall Wheeler, yes, heck. I don't even remember, and developed this into a device now known as the Geiger counter. And so you've probably all seen or seen or heard Geiger counters going off in movies, right? They go ping, 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 right? They bounce off randomly. This is an extremely important lesson, which is tantamount to the lesson of our second experiment yesterday, the 50-50 when we didn't expect it. The white electrons into the hardness box, then into a color box again, come out 50-50, not 100%, and they come out in a way that's unpredictable. We have no ability, to our knowledge, and more than our knowledge, we'll come back to that in Bell's table, we have no ability to predict which electron will come out of that third box, white or black, right? Similarly, with Geiger counter, you hear that atoms decay, but they decay randomly. The radiation comes out of a pile of radioactive material, totally random. We know the probabilistic description of that. We're going to develop that. We don't know exactly when. And that's a really powerful example. Both of those terms are powerful examples of randomness. And so we're going to have to incorporate that into our laws of physics, into our model of quantum phenomena as well. Questions? I usually have a Geiger counter at this point, which is totally awesome. So I'll try to produce the Geiger counter demo later. But the person with the Geiger counter turned out to have left the continent. So made it a little challenging. Okay. It's just sort of, since we're at MIT, an interesting side note. This strategy of so-called hard scattering, of taking some object and sending it at a very high velocity at some other object and looking for the rare events when they bounce off at some large angle, so-called hard scattering, which is used to detect dense cores of objects. It didn't stop with Rutherford. People didn't just give up at that point. Similar experiments in the 60s and 70s, which were conducted at SLAC, involved not alpha particles incident on atoms, but individual electrons incident on protons. So not shooting into the nucleus, but shooting and looking for the effect of hitting individual protons inside the nucleus. And through this process, it was discovered that, in fact, so this was done in the 60s and 70s, that in fact the proton itself is also not a fundamental particle. The proton is itself composite. And in particular, it's made out of, eventually people understood that it's made out of, morally speaking, I'm going to put this in quotation marks, asking about it in office hours, 3 quarks, which are some particles, and the reason, all this tells you is that it's an object we give it as the name quark, but indeed, there are 3 point particles that in some sense make up a proton. It's actually much more complicated than that. But these quarks, among other things, have very strange properties, like they have fractional charge. And this was discovered by a large group of people, in particular led by Kendall and Freeman and also Richard Taylor. Kendall and Freeman were at MIT. Richard Taylor was at Stanford. And in 1990, they shared the Nobel Prize for the discovery of the partonic structure of the nucleons. So these sorts of techniques that people have been using for a very long time continue to be useful and awesome. In particular, the experimental version of this that's currently going on that I particularly love is something called the relativistic heavy ion collider, which is going on in Brookhaven. So here what you're doing is you take 2 protons and you blow them into each other. Okay, at ultra high energy, 2 protons collide them and see what happens. And that's what happens. Okay, you get massive shrapnel coming flying out. So instead of having a simple thing where one particle just bounces back because there's some hard core, instead what happens is just shrapnel everywhere, right? So you might think, well, how do we interpret that at all? How do we make sense out of 14,000 particles coming out of 2 protons bouncing into each other? How does that make any sense? And the answer turns out to be kind of awesome. And so this touches on my research, so I want to make a quick comment on it just for color. The answer turns out to be really interesting. First off, the interior constituents of protons interact very strongly with each other. But at the brief moment when protons collide with each other, what you actually form is not a point like quark and another point like quark. In fact, protons are made out of like quarks at all. Protons are big bags with quarks and gluons and all sorts of particles fluctuating in and out of existence in a complicated fashion. And what you actually get is, amazingly, a liquid. For a brief moment of time, the parts of those protons that overlap, think of them as two spheres and they overlap in some sort of almond-shaped region. The parts of those protons that overlap form a liquid at ultra-high temperature and ultra-high density. It's called the Rick fireball or the Cordillon plasma, although it's not actually a plasma, but it's a liquid like water. What I mean by saying it's a liquid like water, if you push it, it spreads in waves, and like water, it's dissipated. Those waves dissipate. But it's a really funny bit of liquid. Imagine you take a cup of coffee, drink your coffee as I want to do, and it cools down over time. It's very frustrating. So you pour in a little bit of hot coffee, and when you pour in that hot coffee, the system is out of equilibrium. It hasn't thermalized. So what you want is you want to wait for all of the system to wait until it's come to equilibrium. So you get sort of hot or sort of cold, some sort of Goldilocksian. So you can ask, how long does it take for this coffee to come to thermal equilibrium? Well, it takes a while, a few seconds, a few minutes, depending on exactly how you mess with it. But let me ask you a quick question. How does that time scale compare to the time it takes for light to cross your bug? Much slower, right? By orders of magnitude. For this liquid that's formed in the ultra-high energy collision, two protons, the time it takes for the system, which starts out crazy out of equilibrium, all sorts of quarks here and gluons there and stuff flying about, the time it takes for it to come to thermal equilibrium is of order the time it takes for light to cross a little puddle of liquid. This is a crazy liquid. It's called quantum liquid. It has all sorts of wonderful properties. And the best thing about it, to my mind, is that it's very well modeled by black holes, which is a totally separate issue, but it's a fun example. So from these sorts of collisions, we know a great deal about the existence of atoms and randomness. As you can see, that's a fairly random story. Okay, so moving on to more four things. Back to atoms. So let's take it specific to that. I'm not kidding. They're really not related to black holes. I get paid for this. so here's a nice fact. So let's get to atomic spectrum. So to study atomic spectrum, here's the experiment I want to run. The experiment I want to run starts out with a some sort of power plant, and out of the power plant come two wires, right? And I'm going to run these wires across a spark gap, a piece of metal here and a piece of metal here, and put them inside a container which has some gas, like H2 or neon or whatever you want, some simple gas inside here. So got a electric potential established across it. Again, we don't want so much potential that it sparks, but we do want to excite the H2. So we can even make it spark. Doesn't really matter too much. The important thing is we're going to excite the hydrogen, and in exciting the hydrogen, the excited hydrogen is going to send out light. And I'm going to take this light. It doesn't do that if light goes in straight line. So we take the light, and I'm going to shine this on a prism, something I was taught to do by Newton, and metaphorically speaking, and look at the image of this light having passed through the prism. And what you find is you find a very distinct set of patterns. You do not get continuous band. In fact, what you get, I'm going to have a hard time drawing this, so let me draw it down here. I'm not going to draw the intensity of the light incident on the screen on this piece of paper. We really used to use pieces of paper for this, which is kind of awesome, as a function of the wavelength that I'll measure in angstroms. Okay. And what you discover is here's around 1,000 angstroms. You get a bunch of lines. You get these spikes, and they start to spread out. Okay. And then aren't so many. And then at around 3,000, you get another set. And then at around 10,000, you get another set. This is around 10,000. And here's the interesting thing about these. So the discovery of these lines, these are named after a guy named Lyman. These are named after a guy named Balmer. Thank you, Steve Balmer, right? Balmer. And these are passion fruit. So everyone needs a mnemonic, okay? So these people identify these lines and explain very simple something. But here's an interesting fact: if you replace this nuclear power plant with a coal plant, it makes no difference. If you replace this prism by a different prism, it makes no difference to where the lines are. If you change this mechanism of exciting the hydrogen, it makes no difference. As long as it's hydrogen in here, you get the same line, maybe with different intensities, depending on exactly how you do the experiment, you get the same position of the lines. Okay. And that's really tricky. Now, if you use a different chemical, a different gas here, like neon, you get a very different set of lines and a very different effective color. You eyeball this thing. So Balmer, incidentally, and I think this is actually why he got blamed for the particular series. I don't know the history. Balmer noticed, by being, depending on which biography you read, very clever or very obsessed, that these guys, this particular set, could be a wavelength. If you wrote the wavelength and labeled it by the integer n, where n ran from 3 to any positive integer above 3, could be written as 36. So this is pure numerology. 3646 angstroms times the function n squared over n squared minus 4, where n is equal to 3 for integer. Okay, and turns out that you just plug in these integers, you get a very good approximation of this series of lines. This is a Howland tradition, a phenomenological fit to some data. Where did it come from? It came from his creative or obsessed mind. So this is Balmer. And this is specifically for hydrogen gas, H2. Okay. So Rydberg and Ritz, said, well, actually we can do one better. Now that they realized this is true, they looked at the whole sequence and they found a really neat little expression, which is that 1 over the wavelength is equal to a single constant parameter, not just for all these, but for all of them, one single numerical coefficient times 1 over n squared minus 1 over n squared. n is an integer greater than 0 and greater than n. And if you plug in any value of n and any value of m for sufficiently reasonable, you can put in 10 million, you just have to see it, it's way out there. But if you put in, or whether in here, if you put in any value of n and m, you'll get one of these lines. So again, why? As it's said, who ordered that? Okay. So this is experimental result 3 that we're going to have to deal with. When you look at atoms and you look at the spectra of light coming off of them, their spectra are discrete, but they're not just stupidly discrete, they're discrete with real structure, something that begs for an explanation. This is obviously more than numerology because it explains with one general coefficient a tremendous number of spectral lines. And there's a different, and crucially, these both work specifically for hydrogen. For different atoms, you need a totally different formula. But again, there's always some formula that nails those spectral lines. Why? So, speaking of atomic spectra, here's a different experiment. So people notice the following thing. People notice that if you take a piece of metal and you shine light at it, by taking the sun or better yet, these days we use a laser, you shine light on this piece of metal. Something that is done all the time in scatter-back is very useful for heat. We really do use lasers, not the sun, but still continues to be useful for this day. You shine light on a piece of metal, and every once in a while what happens is electrons come flying off. And the more light and the stronger the light you shine, you see changes in the way that electrons bounce off. So we like to measure that, to make that precise. And this was done in a really lovely experiment. Here's the experiment. The basic idea of the experiment is I want to check to see, as I change the features of the light, the intensity, the frequency, whatever, I want to see how that changes the properties of the electrons that bounce off. Now, one obvious feature of an electron that flew off a piece of metal is how fast is it going? How much energy does it have? What's its kinetic energy? So I'd like to build an experiment that measures the kinetic energy of an electron that's been excited through this photoelectric effect, through emission after shining light on a piece of metal. Cool? So I want to build that experiment. So here's how that experiment goes. Well, if this electron comes flying off with some kinetic energy, and I want to measure that kinetic energy, imagine the following circuit. Okay, first off, imagine I just take a second piece of metal over here, and I'm going to put a little current meter here and here. And here's what this circuit does. When I shine light on this piece of metal, we'll put a screen calculator, the electrons come flying off, they get over here. And now I've got a bunch of extra electrons over here, and I'm missing electrons over here. So this is negative, this is positive, and the electrons will now flow along this wire back here to neutralize the system. The more light I shine, the more electrons will go through this circuit. And as a consequence, there will be a current running through this current meter. That cool, everyone? Okay, so we haven't yet measured the kinetic energy, though. How do we measure the kinetic energy? I want to know how much energy with how much energy of these electrons ejected. Well, I can do that by the following clever trick. I'm going to put now a voltage source here, which I can tune the voltage of, okay, with a voltage V. Now what that's going to do is set up a potential difference across these, and the energy in that is the charge times the potential difference. So I know that the potential difference it takes, the amount of energy it takes to overcome this potential difference is Q times V. Is that cool? So now imagine I send in an electron, I send in light, and it leads an electron to jump across, and it has kinetic energy Ke. Well, if the kinetic energy is less than this, will it get across? Not so much. It'll just fall back. But if the kinetic energy is greater than the energy it takes to cross, it'll cross and induce a current. Yeah. So the upshot is that as a function of the voltage, what I should see is that there's some critical minimum voltage, and depending on how you set up the sign could be either way, but there's some critical minimum voltage where for less voltage, the electron doesn't get across, and for any greater voltage.
So I'm just going to pause this. So this experiment here, again, voltage gap. Voltage is like height for gravity, but for electricity. So one way of thinking of it, although he's drawn it schematically, is like it going from the left side to the right side. Another way to think of it is like it's like if you were shooting a ball up, and if it doesn't have enough energy, it won't touch the top and allow itself to continue down the time. So if there is this sort of if the voltage created by this sort of battery or whatever in the circuit is too high, it won't be able to jump up, and you won't be able to complete the circuit when the electron flies free. So this is a way of measuring the kinetic energy.
For any closer to zero voltage, the electron has enough kinetic energy to get across, and so the current should increase. So there's a critical voltage, B critical, where the current running through the system runs to zero. Okay? You make it harder for the electrons by making the voltage in magnitude even larger. Make it harder for the electrons to get across. None will get across. Make it a little easier, more and more will get across, and the current will go up. Cool? Okay, so what you want to do to measure this kinetic energy is you want to measure the critical voltage at which the current goes to zero. So now the question is, what do we expect to see? And remember, the things we can tune in this experiment are the intensity of the light, which is like E squared plus B squared. And we can tune the frequency of the light. We can vary that. Now, does the total energy, does the frequency show up in the total energy of a classical electromagnetic wave? No, if it's an electromagnetic wave, it cancels out. You just get the total intensity, which is the square of the fields. So this is just like a harmonic oscillator. The energy is in the amplitude. The frequency of the oscillator doesn't matter. You push the swing harder, it gets more kinetic energy. It's got more energy. Okay. So what do we expect to see as we vary, for example, the intensity? So here's a natural guess. If you take, so you can think about the light here as getting a person, literally, like get the person next to you to take a bat and hit a piece of metal. Right? If they hit it really excite electrons with a lot of energy, they just blast the heck out of it, then it would be surprising if you get much more energy of the particles that come flying off. Hard enough things are going to shrapnel and energy. So the expectation here is the following: that if you have a more intense beam, then you should get more. The electrons coming out should be more energetic. So you're hitting them harder. And remember that the potential, which I will call V0, the stopping voltage, or sorry, V0, the stopping voltage. So therefore, V0 should be greater in magnitude. So this anticipates that the way this curve should look as we vary the current as a function of V. If we have a low voltage, if we have a low intensity beam, it shouldn't take too much potential to impede motion. But if we have, so this is a low intensity. But if we have a high intensity beam, it should take a really large voltage to impede the electric flow, electric current, because high intensity beam, you're just whacking those electrons really hard, and they're coming off a lot of kinetic energy. So this is high. Everyone down with that intuition? This is what you get from Maxwell's electrodynamics. This is what you'd expect. And in particular, as we vary, so this is our predictions. In particular, as we vary, so this is 1, 2, with greater intensity. And the second prediction is that V naught should be independent of frequency, because the energy density in an electromagnetic wave is independent of the frequency. It just depends on the amplitude. And we'll use nu to denote the frequency. Okay? So those are the predictions that come from 802 and 803. But this is 804. And here's what the experimental results actually look like. So here's the intensity, here's the potential. And if we look at high potential, it turns out that if we look at intermediate potentials, it's true that the high intensity leads to a larger current, and the low intensity leads to a lower current. But here's the funny thing that happens. As you go down to the critical voltage, the critical voltages are the same. What that tells you is that the kinetic energy kicked out, the kinetic energy of an electron kicked out of this piece of metal by light is independent of how intense that beam is. No matter how intense that beam is, no matter how strong the light was shining on the material, the electrons all come out with the same energy. This would be like taking a baseball and hitting it with a really powerful swing or a really weak swing and seeing that the electron dribbles away with the same amount of energy. This is very counterintuitive. But so more surprisingly, so V naught is actually independent of intensity. But here's the real shocker: V naught varies linearly in the frequency. What does change V naught is changing the frequency of the light that's incident. That means that if you take incredibly diffuse light, you barely see it, of a very high frequency, then it takes a lot of energy to impede the electrons that come popping off. The electrons that come popping off have a large energy. But if you take a low frequency light with extremely high intensity, then those electrons are really easy to stop. Powerful beam, but low frequency, it's easy to stop those electrons. Weak, little tiny beam, high frequency, very hard to stop the electrons that do come off. So this is very counterintuitive, and it doesn't fit at all with Maxwellian picture. Questions about that? So this led Einstein to make a prediction. This was his 1905 result. One of his many totally breathtaking papers is that here. And he didn't really propose a model or a detailed theoretical understanding of this, but he proposed a very simple idea. And he said, look, if you want to fit this experiment with some simple equations, here's the way to explain it. I claim that light comes in packets or chunks with definite energy. And the energy is linearly proportional to the frequency. Energy is equal to something times nu, and we'll call the coefficient h. Okay? The intensity of light, or the amplitude squared, the intensity is like the number of atoms. So if you have a more intense beam at the same frequency, the energy of each individual chunk of light is the same. There are just a lot more chunks flying around. And so, to explain the photoelectric effect, Einstein observed the following. Look, he said the electrons are stuck onto the metal, and it takes some work to pull them off. So now, what's the kinetic energy of an electron that comes flying off of the K3? Pardon, I have a laugh about that. K3. So the kinetic energy of an electron that comes flying off, well, it's the energy deposited by the photon, the chunk of light, h nu, but we have to subtract off the work it took, minus the work to extract the electron from the material. You think of this as how much energy does it take to suck it off the surface. Okay. And the consequence of this is that the kinetic energy of an electron should be, look, if h nu is too small, if the frequency is too low, then the kinetic energy would be negative. But that doesn't make any sense. You can't have negative kinetic energy. It's a strictly positive quantity. So it just doesn't work until you have a critical value where the frequency times h, this coefficient, is equal to the work it takes to extract. And after that, the kinetic energy rises with a frequency with a slope equal to h. And that fits the data like a chain. So no matter, let's think about what this is saying here. No matter what you do, if your wave is very low frequency, and you pick some definite piece of metal that has a very definite work function, very definite amount of energy to extract an electron from the surface, no matter how intense you're being, if the frequency is insufficiently high, no electrons come off. None. Right? So it turns out none is maybe a little overstatement, because what you can have is two photon processes, where two chunks hit one electron at the right just at the same time, or roughly speaking, at the same time, and they have twice the energy. But you can imagine that the probability of two photons hitting one electron at the same time is pretty low. So the intensity has to be preposterously high. And you see those sorts of multi-photon effects. But as long as we're not talking about insane high intensities, this is an absolutely fantastic probe of the physics. Now, there's a whole long subsequent story in the development of quantum mechanics about this particular effect, and it turns out the photoelectric effect is a little more complicated than this. But the storyline is a very useful one for organizing your understanding of the photoelectric effect, and in particular, this relation that Einstein proposed out of the blue with no other basis. No one else had ever seen this sort of statement that the electrons, or that the energy of light, the beam of light, should be made up of some number of chunks, each of which has a definite minimum amount of energy. So you can take what you learned from 802 and 803 and extract a little bit more information out of this. So here's something you learned from 802. In 802, you learned that the energy of an electromagnetic wave is equal to 2 times the momentum. And in 803, you should have learned that the wavelength of an electromagnetic wave times the frequency is equal to the speed of light, c. And we just had Einstein tell us, or declare it without further evidence, just saying, look, this fits, that the energy of a chunk of light should be h times the frequency. So if you combine these together, you get another nice relation that's similar to this one, which says that the momentum of a chunk of light is equal to h over lambda. So these are two enormously influential expressions which come out of this argument from the photoelectric effect from Einstein. And they're going to be, their legacy will be with us throughout the rest of the semester. Now this coefficient has a name, and it was named after Planck. It's called Planck's constant. And the reason it's called Planck's constant has nothing to do with photoelectric. It was first this idea that an electromagnetic wave, that light, had an energy which is linearly proportional to its intensity squared, none of that, but just linearly proportional to the frequency, first came up in an analysis of blackbody radiation by Planck. And you'll go through this in some detail in 8044 later in the semester, so I'm not going to dwell on it right now. But I do want to give you a little bit of perspective on it. So Planck ran across this idea that E is equal to h2 through the process of trying to fit an experimental curve. There was a theory of how much energy should be emitted by an object that's hot and glowing as a function of frequency. And that theory turned out to be in total disagreement with the experiment. Spectacular disagreement. The curve for the theory went up, the curve for the experiment went down. They were totally different. So Planck set about writing down a function that described the data. Literally curve fitting. That's all he was doing. And this is the depths of desperation to which he was led. Curve fitting. He's an adult. He shouldn't be doing this, but he was curve fitting. And so he fits the curve, and in order to get it to fit, the only thing that he can get to work, even vaguely well, is if he puts in this calculation of h nu. He says, well, maybe when I sum over all the possible energies, I should restrict the energies proportional to frequency. And it was forced on him because it fit from the function, just functional analysis. Hated it. He completely hated it. He was really frustrated by this. It fit perfectly. He became very famous. He was already famous. He became ridiculously famous. Just totally loathed this idea. Okay? So it's now become a cornerstone of quantum mechanics. But he wasn't so happy about it. And to give you a sense for how bold and punchy this paper by Einstein was, it said, look, seriously, guys, E equals h nu. Here's what Planck had to say when he wrote a letter of recommendation to get Einstein into the Prussian Academy of Sciences in 1913. So he said, there is hardly one among the great problems in physics to which Einstein has not made an important contribution. That he may sometimes have missed the target in his speculations, as in his hypothesis of photons, cannot really be held too much against him. It's not possible to introduce new ideas without occasionally taking a risk. Einstein, who subsequently went on to develop special relativity and general relativity and prove the existence of atoms and the best measurement of Avogadro's constant, subsequently got the Nobel Prize, not for Avogadro's constant, not for proving the existence of atoms, not for relativity, but for photons. Because of guys like Planck, right? This is crazy. So this was a pretty bold idea. And here you get a sense for why. Let me leave that up because it's just sort of fun to see these guys scowling and smiling. Incidentally, there's a great book about Einstein's years in Berlin by Tom Levinson, who's a professor here, a great writer and a historian of science. You should take a class with him, which is really great. But I encourage you to read this book. It talks about why Planck is not looking so pleased right now, among many other things. It's a great story. So let's step back for a second. Why was Planck so upset by this? And why was, in fact, everyone so flustered by this idea that it led to, the best prize you can get of a physicist? Apart from a happy home, I've got that one. That's the one that matters to me. So why? Why is this so surprising? And the answer is really simple. We know that it's false. We know empirically. We've known for 200 and some years that light is a wave. Empirically. This isn't like, I think it'd be nice if it was a wave. It's a wave. So how do we know that? So this goes back to the double slit experiment from Young. Young's performance of this was in 1803. Intimations of it come much earlier, but this is really where it gets nailed to the wall. And here's the experiment. So how many people in here have not seen a double slit experiment this round? Yeah, exactly. Okay, so I'm just going to quickly remind you of how this goes. So we have a source for waves. We let the waves get big until they're basically plane waves, and we take a barrier and we pump 2 slits in it. And these plane waves they act like sources of the slits, so we get new, and you get crests and troughs, and you'll get some distant screen, and you'll get pattern. The pattern you get has a maximum, but then it falls off, and it has the wiggles, these interference ranges. And these interference ranges are, of course, extremely important. And what's going on here is that the waves sometimes add in, so the amplitude, the height of the wave, sometimes adds constructively and sometimes destructively. So that sometimes you get twice the height and sometimes you get nothing. Okay. So just because it's fun to see this, here's Young's actual diagram from his original note on the double slit experiment. It's like this is so A and B of the slits, and C, D, and F of on the screen, the distant screen. Drew by hand. Pretty good. So we've known for a very long time that light, because of the double slit experiment, light is clearly a wave, behaves like a wave. What are the senses in which it behaves like a wave? There are 2 important senses here. The first is answered by the question, where did the wave hit the screen? Okay. So when we send in a wave, I drop a stone, one big pulsing wave comes out, it splits into, it leads to new waves being instigated here and interfere. Where did that wave hit the screen? Anyway. Yeah, exactly. It didn't hit this wave at the screen at any one point. Some amplitude shows up everywhere. The wave is a distributed object. It does not exist at one spot. And it's by virtue of the fact that it is not a localized object, it is not a point-like object, that it can interfere with itself. Right? The wave is a big, large phenomena in a liquid, in something. So it's sort of essential that it's not a localized object. So not localized. The answer is not localized. And let's contrast this with what happens if you take this double slit experiment and you do it with, I don't know, take who? Tim Wakefield. Let's give some up to that guy. So baseball player, and have him throw baseballs at a screen with 2 slits in it. Okay, and he's got pretty good. He's got terrible accuracy actually. So every once in a while he'll make it through the slit. So let's imagine first blocking out when he's a knuckleballer. So every once in a while the baseball will go through the slit. And let's think about what happens. We'll cover one slit. And what we expect to happen is, well, it'll go through more or less straight, but sometimes it'll scrape the edge and it'll go off to the side. Sometimes it'll come over here. But if you take a whole bunch of baseballs, and so any one baseball, where does it hit? Some spot. Right, one spot, not distributed, one spot, and as a consequence, one goes here, one goes there, one goes there, and now there's nothing like interference effects. But what happens is, you get some distribution if you look at where they all hit. Yeah, ever cool with that? And if we had covered over this slot or slit and let the baseballs go through this one, same thing would happen. Now, if we leave them both open, what happens is sometimes it goes here, sometimes it goes here. Now it's pretty useful. We've got a knuckleballer, and what you actually get is the total distribution looks like this. It's the sum of the 2. But at any given time, any one baseball, you say, the baseball either went through the top slit, and more or less goes up here, or went through the bottom slit, and more or less goes down here. Right? So for chunks, so this is for waves, for chunks, for localized particles, they are localized. And as a consequence, we get no interference. So for waves, they are not localized, and we do get interference. Interference. Okay. So on your problem set, you're going to deal with some calculations involving these interference effects, and I'm going to brush over that. Anyway, the point of these the double slit experiment is that whatever else you want to say about baseballs or anything else, light, as we've learned since 1803 in Young's double slit experiment, light behaves like a wave. It is not localized. It hits the screen over its entire extent, and as a consequence, we get interference. The amplitudes add. The intensity is the square of the amplitude. If the intensities add, if the amplitudes add, amplitude total is equal to A1 plus A2. The intensity, which is the square of A1 plus A2 squared, has interference terms, the cross terms from this square. So, where am I? So light, from this point of view, is an electromagnetic wave. It interferes with itself. It's made of chunks, and I can't help but think about it this way. This is literally the metaphor I use in my head. Light is creamy and smooth like a wave. Chunks are very different. But here's the funny thing: light is both smooth like a wave. It is also chunky. It is super chunky, as we have learned from the photoelectric effect. Okay, so light is both at once. So it's the best of both worlds, right? It's, everyone will be satisfied, or unless you're not from the US, in case this is deeply disturbing. So, of course, the original super chunk is banned. So we learned now from Young that light is a wave. We learned from the photoelectric effect that light is a bunch of chunks. Okay, both experimental results are true. So how does that work? Well, we're gonna have to deal with that. But enough about light. If this is true of light, depending on what experiment you do and how you do the experiment, sometimes it seems like it's a wave, sometimes it seems like it's a chunk or particle, which is true, which is the better description. So it's actually worthwhile to not think about light all the time. Let's think about something more general. Let's stick to electrons. So as we saw from yesterday's lecture, you probably want to be a little bit wary when thinking about individual electrons. Things could be a little bit different in your classical intuition. But here's a crucial thing. Before doing anything else, we just think, which one of these two is more likely to describe electrons well? Well, electrons are localized. When you throw an electron at a CRT, it does not hit the whole CRT with a weighting distribution. When you take a single electron, you throw it at a CRT, it goes ping, and there's only a glowing spot. Electrons are localized. And we know that localized things don't lead to interference. Right. Some guys at Hitachi, really good scientists and engineers, developed some really awesome technology a couple of decades ago. They were trying to figure out a good way to demonstrate their technology. And they decided that, it would be really awesome. This thought experiment that people always talk about, that's never been done really well, of sending an electron through two slits. In this case, it was like 10 slits. Effectively, it was crazy. Send an electron through a bunch of electrons, one at a time, throw the electron weight, like our French guy with the boat. So, do this experiment with our technology, and let's see what happens. Okay? And this really is one of my favorites. This is one of, let's see how we close these screens. Aha. Okay, this is going to take a little bit of, and it's broken. Oh, no. Oh, that's so sad. Oh. Come on. Oh, I'm just gonna let. Yeah. Let's see if we can get part of the way. I want to destroy it. So what they actually did is they said, we want to see what happens. Because we're so awesome at Hitachi research labs. Let's do it. So here's what they did, and I'm going to turn off the lights. Great. Okay, and I set this to some music because I like it. Okay, here's what's happening. One at a time, individual photons.
I'm just gonna mute it because I just don't want YouTube to take down this feed if I'm playing it here.
Those guys know what they're doing. There we go. So I don't know of a more vivid example. It's totally obvious. You see individual electrons, they run through the apparatus, you wait. They run through the apparatus, you wait. One at a time, single electron, like a baseball being pitched through two slits. And what you see is an interference effect. But you don't see the interference effect like you do from light. You don't get from waves on the sea. You see the interference effect by looking at the cumulative stacking up of all the electrons as they hit, where all the electrons hit one at a time. So, is an electron behaving like a wave in a pond? No, I'm just a wave in a pond hit at a spot. No, it's a distributed beast. Okay, yes, it interferes, but it's not localized. Well, is it behaving like a baseball? Well, it's localized. But when I look at a whole bunch of electrons, they do that. They seem to interfere, but there's only one electron going through at a time, so it's something that's interfering with itself. How does that work? Is an electron a wave? Does an electron hit at many spots at once? No. So is an electron a wave? No. Is an electron a baseball? No. It's an electron. Okay? So this is something we're going to have to deal with. That every once in a while, we have these wonderful moments where it's useful to think about an electron as behaving in a wave-like sense. Sometimes it's useful to think about it as behaving in a particle-like sense. But it is not a particle like you normally conceive of a baseball. And it is not a wave like you normally conceive of a wave on the surface of a pond. It's an electron. Let's see if we get... I like to think about this like an elephant. If you're closing your eyes and you walk up to an elephant, you might think like a sand, you kind of got a tree trunk, there's a fan over here. And who knows, like maybe it's a wave, maybe it's a particle, I can't really tell. But if you could just see the thing the way it is, not through the preconceived sort of notions you have, you see it's an elephant. Yes, that is the data center. So, look, everything has to happen sometime, right? so Heisenberg, people often give the false impression in popular quantum physics, so I want to subvert this, that in the early days of quantum mechanics, the early people like Bohr and Oppenheimer and Heisenberg, who invented quantum mechanics, they were really tortured about, is an electron, it's a wave particle duality, it's both. And this is one of the best subversions of that sort of silliness that I know of. So what Heisenberg says, the two mental pictures which experiments lead us to form, the one of particles, the other of waves, are both incomplete and have only the validity of analogies, which are accurate only in limiting cases. The apparent duality arises in the limitation of our language. Okay? And then he goes on to say, look, you develop your intuition by throwing rocks and, swimming. And that's not going to be very good for atoms. So this will be posted. It's really wonderful. His whole lecture is really, the lecture is really quite lovely. And that's, by the way, that's him in the middle there, Polly all the way on the right. I guess they were pleased. Okay, so that's the Hitachi thing. So now let's pick up on this though. Let's pick up on this and think about what happens. I want to think in a little more detail about this Hitachi experiment, and I want to think about it in the context of a simple two-slit experiment. So here's our source of electrons. It's a literally a gun, an electron gun, and it's firing off electrons. And here's our barrier, and it has two slits in it. Okay, and we know that any individual electron hits its own spot, right? But when we take many of them, we get an interference effect. We get interference fringes. So the number that hit a given spot. Hello. Construct this distribution. So here's the question I want to ask. When I take a single electron, I shoot one electron at a time through this experiment, one electron. You can go through the top slit, you can go through the bottom slit. While it's inside the apparatus, which path does it take? Good. So did it take the top path? How do you know? Good. Let's block the bottom, okay, to force it to go through the top slit. So we'll block the bottom slit. Now, when the only electrons that make it through, go through the top slit. Okay, half of them don't make it through. But those that do make it through give you this distribution. No interference. But I didn't tell you these are hundreds of thousands of kilometers apart. The person who threw in the electron didn't know whether there was a barrier here. The electron, how could it possibly know whether there was a barrier here from the top? This is exactly like our boxes. Right? It's exactly like our box. Did it go through an electron when the slits are both open? And we know that ensemble average, it will give us an interference effect. Did the electron inside the apparatus go through the top path? No, did it go through the bottom path? Did it go through both? Because we only see one electron. Did it go through neither? It is in of having gone through the top and the bottom, being along the top path and being along the bottom path. This is a classic example of the two-box experiment. Okay. So I want to tie that together. So let's nuance this just a little bit, though, because it's going to have an interesting implication for gravity. Okay, here's the nuance I want to pull in this one. Let's cheat. Okay, suppose I want to measure which slit the electron actually did go through. How might I do that? Well, I can do the coarse thing of negotiation. I can block it, just catch the electrons that go through in that spot. But that's a little heavy-handed. Probably I can do something a little more delicate. And so here's the more delicate thing I'm going to do. I want to build a detector, okay, that uses very, very, very weak light, extremely weak light, to detect whether the particle went through here or here. The way I can do that is I can sort of shine light through, and at each point I'm going to bounce. So here's my source of light, and I'll be able to tell whether the electron went through this slit or went through this slit. Cool. So imagine I did that. So obviously I don't want to use some giant, huge, ultra-high energy laser because it would just blast the thing on the way. It would sort of be I want to use something very diffuse, very low energy, very low intensity, electromagnetic wave. And the idea here is that, okay, it's true that when I bounce this light off an electron, let's say it bounces off an electron here, it's true, it's going to, impart some momentum and the electron's going to achieve source, but if it's really, really weak, low energy light, then it's going to, it's going to deflect it only a little tiny bit. So it will change the pattern I get over here. But it'll change it in some relatively minor way because I've just thrown in very, very low energy light. Yeah, that makes sense? So this is the experiment I want to do. This experiment doesn't work. Why? No, it's true that, it turns out that those are correlated fact, but here's the problem. I run this experiment without anyone actually knowing what happens until long afterwards. So knowing doesn't seem to play any role. It turns out it's very tempting often to say no, but it turns out that it's really not all you know. It's really just what the experiment you're doing. So what principle that we've already run into today makes it impossible to make this work? I want to shine really low energy, really diffuse light through and have it scatter weakly. Yeah. Yeah, exactly. That's exactly right. So when I say really low energy, I really can't mean, because we've already done this experiment, I cannot possibly mean low intensity, because intensity doesn't control the energy imparted by the light. But the thing that controls the energy imparted by a collision of the light with the electron is the frequency. The energy in that chunk of light is proportional to the frequency. So now if I want to make the effect, the energy, or the momentum, similarly, the momentum we're going to do. Remember, the momentum goes like h over lambda. If I want to make the energy really low, I need to make the frequency really low. If I want to make the momentum really low, I need to make the wavelength what? Really big. Right? So in order to make momentum imparted by this photon really low, I need to make the wavelength really long. But now here's the problem. If I make the wavelength really long, so if I use a really long wavelength wave, like this long wavelength, are you ever going to be able to tell which slit it went through? No, because particles could have been anywhere. Because scattered this light if it was here, if it was here, if it was here. Right? In order to measure where the electron is to some reasonable precision, it's sort of down to this sort of wavelength. I need to be able to send in light with a wavelength that's comparable to the scale that I want to measure. Okay? And it turns out that if you run through and just do the calculation, suppose I send in, and this is done in the books, I think all four, but this is done in the books on the reading list. If you send in a wave with a short enough wavelength to be able to distinguish between these two slits, which slit did it go through, the momentum that it imparts precisely washes out, is just enough to wash out the interference effect and break up these fringes so you don't see interference effects. It's not about what you know, it's about the particulate nature of light and the fact that the momentum of a chunk of light goes like h over lambda. Okay? But this tells you something really interesting. Did I have to use light to do this right now? I could have sent in anything, right? I didn't have to bounce light off these things. I could have bounced off, gravitational waves. So if I had a gravitational wave detector, so Matt works on gravitational wave detectors, and so I didn't tell you this, but Matt gave me a pretty killer gravitational wave detector. Here it is. There's my awesome gravitational wave detector. And now I'm going to build supernova, okay? And they're creeping on this black hole is going to create giant gravitational waves. I'm going to use those gravitational waves and detect them with super advanced LIGO, and I'm going to detect which fluid went through. But gravitational waves, those aren't photons, so I really can make a low intensity gravitational wave, and then I can tell which fluid went through without destroying the interference effect. Right? That would be awesome. What does that tell you about gravitational waves? They must come in chunks, right? In order for this all to fit together logically, you need all the interactions that you could scatter off of this to satisfy these quantization properties. But the energy is proportional to the frequency. Now, the line I just gave you is a heuristic, and making it precise is one of the great challenges of sort of modern contemporary high energy physics, of dealing with the quantum mechanics and gravity together. But this gives you a strong picture of why we need to treat all forces and all interactions quantum mechanically in order for the world to be consistent. Okay. Good. Okay. Questions at this point? Okay. Oh. I forgot about this one. So there are actually two more. So I want to just quickly show you. Okay. So this is a gorgeous experiment. So remember I told you the story of the guy with the boat and the opaque wall. And it turns out that's a cheat. It turns out that that this opaque screen doesn't actually give you quantum mechanically isolated photons. They're still in a very important way classical. So this experiment was done truly with a source that gives you quantum mechanically isolated single photons one at a time. So this is the analog of the Hitachi experiment. And it was done with pretty awesome Japanese here some number of years ago. And I just want to emphasize to give you exactly the same effects. We see that photons, this should look exactly like that we saw at the end of the video. And that's because it's exactly the same physics. It's a grating with something like 10 slits, and individual particles going through one at a time and hitting the screen one bing. So what you see is the light going bing on the CCD. It's a pretty spectacular experiment. Okay, so let's get back to electrons. I want to know whether electrons are really waves or not. So this other experiment, again, you're going to study this on your problem set. This other experiment was done by a couple of characters named Davison and Germer. And in this experiment, what they did is they took a crystal, and a crystal is just a lattice of regularly located ions. Yeah. These what, sir? You mean for different electrons? Well, they can be different if the initial conditions are different. But they could be, if the initial conditions are the same, then the probabilities are identical. Yeah, so every electron behaves identically to every other electron in that sense. Is that what you're asking? Yeah. Sure. Oh, absolutely. So the issue there is just a technological one of trying to build a beam that's perfectly collimated, and that's just not doable. So there's always some dispersion in the beam. So in practice, it's very hard to make them identical. But in principle, it could be if you were infinitely powerful as an experimentalist. Again, it was made from a lab, so it's not me. So here's our crystal. You can think of this as diamond or nickel or whatever. I think they actually use nickel, but I don't remember exactly. And they sent in a beam of electrons. They send in a beam of electrons, and what they discover is that if you send in these electrons and watch how they scatter at various different angles, I'm going to call the angle here of scattering theta. What they discover is that the intensity, the intensity of the reflected beam as a function of theta shows interference effects. And in particular, they gave a whole calculation for this, which I'm not going to go through right now, because it's not terribly germane for us. You're going to go through it on your problem set, so that would be good, and so everything for your recitation structures we go through. But the important thing is the offshot. So if the distance between these crystal planes is L, D, we call it D. The distance between the crystal planes is D. What they discover is that the interference effects that they observed, these maximum and minima, are consistent with the wavelength of light, with the electrons behaving as if they were waves, with a definite wavelength, with a wavelength lambda being equal to some integer n over 2d sine theta. So this is the data these are the data they actually saw. Theta are plural. These are the data they actually saw. And they infer from this that the electrons are behaving as if they were wave-like with this wavelength. And what they actually see are individual electrons hitting one by one, although in their experiment they couldn't resolve individual electrons. But that is what they see. And so in particular, putting all this back into the experiment, you send in the electrons with some energy, which corresponds to some definite momentum. This leads us back to the same expression as before, that the momentum is equal to h over lambda with this lambda associated. So it turns out that this is correct. So the electrons diffract off the crystal as if they have no momentum, which comes with a definite wavelength corresponding to its momentum. So that's experimental result. Oh, I forgot to check out 4. That's experimental result 5, that electrons diffract. We already saw electron diffraction. So something to emphasize is that, so these experiences we've described were done with photons and with electrons, but you can imagine doing the experiments operable. This is, of course, hard. Quantum effects for microscopic objects are usually insignificantly small. However, this experiment was done with buckyballs, which are the same shape as soccer balls in some sense, but they're huge. They're gigantic objects. And so here's the experiment in which this was actually done. These guys are just totally. So this is Elmer's lab, and it doesn't look like. Well, I mean, it looks kind of, it's hideous, right? I mean, to a theorist, it's like, come on, you gotta be kidding. But here's what the theorist is happy about, because it looks simple. We really love lying to ourselves about that. So here's an oven. We're going to cook up some buckyballs and hit them with some definite known thermal energy, known to some accuracy. We're going to collimate them by sending them through a single slit, and then we're going to send them through a diffraction grating, which again is just a whole bunch of slits. And then we're going to image them using photoionization and see where they pop through. So here is the horizontal position this way along the grading, and this is the number that come through. So literally one by one count, bing as the C60 molecule goes through. So without the grading, you just get a peak, but with the grading, you get these side bands, you get interference ranges. So these guys, again, they're going through one by one. A single buckyball, 60 carbons, going through one by one is interfering with itself. This is a gigantic object by any sort of comparison to single electrons, and we're seeing these interference ranges. So this is a pretty tour de force experiment, but I just want to emphasize that if you could do this with your neighbor, it would work. You just have to isolate the system well enough, and that's a technological challenge, but not an principal one. Okay, and yeah, good. Okay, so we have one last experimental fact to deal with, and this is Bell's inequality, and this is my favorite one. So Bell's inequality for many years languished in obscurity until someone realized that it could actually be done beautifully in an experimental, a very concrete experiment that they could actually do what they wanted to do, and we now think of it as an enormously influential idea, which nails the coffin closed for classical mechanics. And it starts with a very simple question. I claim that the following inequality is true: the number of people in the room who are undergraduates, which I'll denote as U, and not blonde, which I denote as RD. So undergraduates who are not blonde. Actually, let me raise this up in English, it's easier. The number who are undergrads and not blonde, plus the number of people in the room who are blonde, but not from Massachusetts, is strictly greater than or equal to the number of people in the room who are undergraduates and not from Massachusetts. I claim that this is true. I haven't checked in this room, but I claim this is true. Let's check. How many people are undergraduates who are not blonde? This is gonna. Jeez. Okay, that's. Yeah, so lots.
Okay, let's just pause and go over why this would be true. So the people who are undergrads and not blonde. So this would be, so supposing this is undergrad, supposing this is blonde, and supposing this is Massachusetts, from Massachusetts. So what these things are saying, maybe I'll just take out a colored one. I'll just take a blue pen. Do I have a blue pen here? I'll do it with pencil. It's fine. So what this is saying, so that undergrads who are not blonde is in this thing. So this is this one. So I'll just draw this here. And blonde, but not from Massachusetts, is this one. So I'm going to just go like this. Okay. And this is going to be number of people who are undergrad and not Massachusetts is going to be undergrad and not Massachusetts is going to be this set here, which I will just, well, I've got a yellow highlighter. Let's see if I can do this without making a mess. All right. So if I'm not mistaken, that should be this right here. So this saying is basically that this number plus this number, which of course includes this mutual overlap, has to be greater than or equal to this number, which seems to make sense, right? Like this seems to make sense that this thing here is wholly contained within the overlap of these two sets. So unless these two sets were completely undone, this should be like we don't have any of the this is only in the undergrads and also not Massachusetts, and this is undergrads and not undergrads and not blonde, but then also blonde and not Massachusetts. So this should completely cover it. Okay, so that's basically what we should assume.
How many people are blonde but not from Massachusetts? Okay, a smattering. Oh God, this is actually going to be terrible.
Oh, I should push this up.
Shoot. undergraduates are not from Massachusetts. Yeah, this is, oh god, this counting is going to be. So I'm going to do this just so I can do the counting of the first two rows here. Okay, my life is going to be easier this way. So how many people in the first two rows in this intersection are undergraduates but not blonde? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We can dispute some of those, but we'll take it for the moment. So 14, I should probably roll it better. So blonde and not from Massachusetts. 1. Awesome. Undergraduates not from Massachusetts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Equality. Okay, so that and you might say, well, look, you should have been nervous there. And admittedly, sometimes there's experimental error. But I want to convince you that I should never, ever be nervous about this moment in a 4. And the reason is the following. I'm going to prove this for you. The way to prove it is slightly more general. And more generally, I want to prove to you that the number of, if I have a set, the number of people who are undergraduates and not blonde, I'll write as B bar, plus the number who are blonde but not from Massachusetts, is greater than or equal to the number that are undergraduates and not from Massachusetts. So how do I prove this? Well, if you're an undergraduate and not blonde, you may or you may not be from Massachusetts. So this is equal to the number of undergraduates who are not blonde and are from Massachusetts, plus the number of undergraduates who are not blonde and are not from Massachusetts. It could hardly be otherwise. You either are or you are not from Massachusetts. Not the sort of thing in machine physics. So this is the number of people who are blonde and not from Massachusetts. Number of people who are blonde, so if you're blonde and not from Massachusetts, you may or may not be an undergraduate. So this is the number of people who are undergraduates, blonde, and not from Massachusetts, plus the number of people who are not undergraduates, are blonde, and are not from Massachusetts. On the right-hand side, so adding these two together gives us plus and plus. On the right-hand side, the number of people who are undergraduates and not from Massachusetts, well, each one could be either blonde or not blonde. So this is equal to the number that are undergraduates, blonde, and not from Massachusetts, plus the number that are undergraduates, not blonde, and not from Massachusetts. Agreed? I am now going to use the awesome power of, and so this is what we want to prove. Now use the awesome power of subtraction, and note that U, B, M bar, these guys cancel, and U, B bar, M bar, these guys cancel. And we're left with the following proposition. The number of undergraduates who are not blonde but are from Massachusetts, plus the number of not undergraduates who are blonde but not from Massachusetts, must be greater than or equal to 0. Can you have a number of people in a room satisfying some condition be less than 0? Can -3 of you be blonde undergraduates not from Massachusetts?
So let's just match these and make it so it's right. This is UBM. So we'll subtract. This is UBM. So it's saying that this is greater than 0, which is what he said.
Not so much. This is a strictly positive number because it's enumerative. It's a counting problem. How many are undergraduates not blonde and from Massachusetts? Yeah? Everyone cool with that? So it could hardly have been otherwise. It had to work out like this. And here's the more general statement. The more general statement is that the number of people, or the number of elements of any set, where each element in that set has binary properties A, B, and C, A or not A, B or not B, C or not C, satisfies the following inequality. Number who are A but not B, plus the number who are B but not C, is greater than or equal to the number who are A but not C. And this is exactly the same argument. And this inequality, which is a tautology really, is called Bell's inequality. And it's obviously true. What did I use to derive this? Logic and integers. Right? I mean, that's bedrock stuff. Here's the problem. I didn't mention this last time, but in fact, electrons have a third property in addition to hardness and color. The third property is called whimsy, and you can either be whimsical or not whimsical. And every electron, when measured, is either whimsical or not whimsical. You never have a boring electron. You never have a ambiguous electron. Always whimsical or not whimsical. So we have hardness, we have color, we have whimsy. Okay? And I can perform the following experiment. From a set of electrons, I can measure the number that are hard, hard and not black, and plus the number that are black, but not whimsical. And I can measure the number that are hard and not whimsical. Okay? And I want to just open up the case a little bit and tell you that the hardness here really is the angular momentum of the electron along the x-axis. Color is the angular momentum of the electron along the y-axis. And whimsy is the angular momentum of the electron along the z-axis. These are things I can measure because I can measure angular momentum. So I can perform this experiment with electrons, and it needn't be satisfied. In particular, we will show that the number of electrons, just to be very precise, the number of electrons in a given set which have positive angular momentum along the x-axis and down along the y-axis, plus up along the y-axis and down along the z-axis, is less than the number that are up. Actually, let me do this in a very clear way. Up 0 down at theta, up at theta, down at 2 theta is greater than the number that are up at 0 and down at theta. Now here's the thing, 2 theta. You can't at the moment understand what this equation means. But if I just tell you that these are 3 binary properties of the electron, okay, and that it violates this inequality, there is something deeply troubling about this result. Bell's inequality, which we proved trivially using integers, using logic, is false in quantum mechanics. And it's not just false in quantum mechanics. We will, at the end of the course, derive the quantum mechanical prediction for this result and show that it leads to a predicted violation of Bell's inequality. This experiment has been done, and the real world violates Bell's inequality. Logic and integers and adding probabilities, as we have done, is misguided. And our job, which we will begin with the next lecture, is to find a better way to add probabilities than classically. And that would be quantum mechanics. See you on Tuesday.
All right, so I have finished one more class. I'm going to just hold on a second. I'll just switch back to this screen here. So, all right, we're down 2 lectures. So I'm just going to close this book and talk a little bit about what we talked about in this lecture here. There we go, quantum physics, give it a little title here. So what did we learn in this lecture? Well, we learned that there are some facts of life that we have to kind of put into our picture. So one of them is that there are atoms. Another one that was talked about was, let me see if I can remember, I believe there were 6 of them. I'm going to go backwards because I'll remember it from that order. So one of them was Bell's inequality. One of them was electron diffraction. One of them was the photoelectric effect. One of them was, what else did we cover? Photoelectric effect, randomness exists. I'm forgetting number 3. What was number 3? Atomic spectra. So I'll just go through all of them briefly. So the first one, that atoms exist. So this has been known for a long time. This is not really that clever, but you can smash things into each other. In this particular case, you talked about foil experiments where you send beams of electrons and they bounce off the foil, meaning that there's this sort of idea that there's these electrons which have a solid, very small positive nucleus and then kind of a negatively charged sort of atmosphere around it. And in particular, there's a kind of naive model of this, which is like a planet where it orbits. This is actually problem set 1 that we covered this morning, and we had to talk about that. And the idea basically being that because of Maxwell's equations, when electrically charged things accelerate, which is something that is going in a circular motion is always doing, they will radiate off photons or radiate off light. And because they're radiating off light, it will rapidly collapse in on itself. So it's not stable. So that's the first thing. The second thing they talked about was randomness exists. And this was what we talked about in the first lecture, basically that you can do these experiments where it will be out slot 1 or slot B. They were talking about hard, soft, which we now have learned are code names for angular momenta in the 3 cardinal directions. And basically, there's no way of knowing which way it's going to come out beforehand unless you have measured that property and you haven't done any intervening measurements. It is random. There's no way of guessing which ones are going to be up or down or hard or soft. The third thing was atomic spectra. Basically, you excite hydrogen atoms and you let them emit photons. They go back down to their state and they release photons in very specific spectra, these discrete lines. So rather than light being all smooth and continuous, it's happening at very specific intervals. So this is something that we need to accommodate for in our theory. Number 4 was the photoelectric effect. So I briefly mentioned this before when I was doing the problem sets, but basically the photoelectric effect shines some light at some metal, electrons will bounce off of it, and you can conduct a very neat experiment where you basically put some voltage between 2 electric plates, one that's getting shined with light, one that's getting the incipient electrons bouncing on it. And you can, by fine-tuning the voltage, make it so that you can tell exactly how much kinetic energy those electrons had. So basically, if you think about like you're throwing a ball up, it will just make it so that you get the height of the other plate just so that it's the height that the balls are going, so that you can measure the exact amount of energy they had, that they're just touching the plate. And so if you're doing it that way, what we find is that the intensity of the light, so a brighter light, has no impact on the kinetic energy of the electrons. It has an impact on the number of electrons that get released. And the only thing that has an impact is the frequency, which is somewhat surprising. This is not an expected result. And then we went and we talked about what was after the photoelectric effect. After the photoelectric effect, we talked about, I just said it, now I'm blanking. Photoelectric effect, and then there's Bell's inequality. Diffraction. So diffraction experiments are the classic double slit. You have 2 slits in things, and the waves will radiate outwards. When crests meet crests, you get a super crest. When troughs meet troughs, you get a super trough. When a crest meets a trough, they cancel out. And this is just wave phenomena. This is something you could see if you had water, and this is true of light. And the interesting thing is, even if you send through photons one at a time, which make definable little dots on the screen, or electrons one at a time, which make little dots, one at a time, they still form this sort of diffraction pattern, which is again surprising, because what is it interfering with? It's interfering with itself, I guess. The final thing is the Bell's inequality, which I always had a really hard time understanding this. They talked about this in some of the like popular books on quantum mechanics that I read. They would talk about Bell's inequality, and I was always like, wait, what? Because it's always like not this and plus this and this, and then it's supposed to be obvious that this. So I thought he did a really good job explaining it, basically that, and I drew it out in circles, that if you take these 2 sets and you consider how the components, that if you were to consider something that has these 3 properties, A, B, and C, that it should hold to this equality, and you can design quantum mechanical experiments which don't work this way, which seem to indicate that at least how we're considering probabilities doesn't quite work in quantum mechanics. But of course, that wasn't really explained how it works in quantum mechanics. We've been hinting at this superposition idea, which I'm interested in getting into, and I'm excited about learning more of that. So I'm going to just take a second and just go through some of the comments that maybe people were making in the chat. I know I don't pay attention much when I'm doing the lectures, just because it's hard to go back and forth. But what are some of the people saying? And he says, this is not an April Fool's joke. Yeah, this is probably my bad. I don't normally do April Fool's jokes. Maybe I should start doing them just to throw you guys off guard now. But maybe launching April 1st, I totally forgot that it was even April Fool's until I started seeing April Fool's jokes. So yeah, I'm boring. I'm actually doing this. What do we see here? Yeah, so some people are saying about watching the lectures and solving the projects are very different things. I'm going to be doing the assignments. Don't worry. This lectures is just to get started. I'm doing the whole thing. So I'm not just filming myself watching the lectures and then calling it a day. One person saying, it seems like you don't like studying. You consider studying like a task that you had to do quickly. So for me, I like the challenge of it. Now, I don't always do things like this. I like to go a little slower and take my time sometimes when I'm just learning things casually. But I kind of like the idea of trying to learn as much as I can with the constraints provided. How can you do it efficiently? So this is a thing that I actually really like. And so it's not about getting it over like a Band-Aid. Rather, it's how can you get more of it? And so maybe that's just me, and I don't, that's just my impression for doing it. But you know, I only have a certain amount of time in the day. I have to work. I have to do this and this. I want to get as much out of I can, and as much as I can out of this class. So let's just look at the notes just real briefly to see if I missed anything. This little, it's called free recall, what I'm doing right now. And I'm just doing it not because I really need to memorize things, but just because I want to make sure that I'm not missing anything important from the lectures. So let's go through what we kind of covered in the notes so far. So again, the atoms exist. I did get all 6 of the things we talked about, the randomness, the atomic spectra. I mean, there was some formula here, particularly the formula for, so that's one thing I didn't recall specifically, was the formula for the momentum of photons. So that's going to obviously come into play in the problem sets. Photoelectric effect, describing that experiment, diffraction, and then Bell's inequality here, which you can see is this little undergrad blonde from Massachusetts, these little intersecting curves that the pencil and the pen completely cover over the highlighted section, which is what you would expect. And if you do the math down here, you see that that follows, and yet that doesn't work for quantum mechanics, which is super crazy, and that's kind of fun. So I'm going to go on to lecture 3 now. I think I have about an hour and 15 minutes left, so we should be pretty good for getting through 3 classes today, which I like. I mean, I'm going through them at 1.5 times the speed, so I might not be able to do that the whole course, so it's good to get it done first now. As for, oh, someone asked me what pen I'm using. These are Muji pens. I love these pens. So I'll just show it here, Muji. They don't pay me, I'm not sponsored or anything. I just love these pens. So without further ado, I will jump in on the next lecture. Someone asked me, what's your motivation for doing this particular challenge? So I'm not going to try to talk about that every time it gets asked because it's going to take up too much time. But if you go to my blog right now, I have a post where I talk about why I want to do this and what's interesting to me about learning quantum mechanics. So let's get lecture 3 up.
The following content is
Okay, and I'm hoping I'm going to get faster with switching all these things. The wave function. Okay, all right. And so I'm going to try to find a way of, I don't like seeing my screen too much because I find it kind of distracting watching 2 versions of the video, but I also try not to move this around too much. I've been kind of moving it around just so that I can make sure my notes are visible on the camera. So this will prevent me from seeing 3 versions of the video, which I find distracting, but I can also see the chat. I can also see the notepad. I'm still getting used to this live streaming stuff. Hopefully it'll be a little smoother in the future. All right, let's do it.
provided under a Creative Commons license. MIT Open Core. Offer high quality educational resources for free.
They usually have a lot of preamble at the beginning of the classes, so I'm going to go a bit faster.
MIT Open Courseware at ocw.mit.edu.
So today, before we get into the meat of today's lecture, Matt has very kindly, Professor Evans, has very kindly agreed to
Then I'm going to
an
just flip over
experiment.
to a new page.
Yeah. So for those of you all who are in recitations, both he and Gordon talked about polarization in recitation last week, and Matt will pick it up from there.
So, back to the ancient past, this was a week ago. We had our hyper-intelligent monkeys that were sorting things that all seemed very theoretical. And in recitation, I said things about polarizers and said, look, if we use polarizers, we can do exactly the same thing as these monkeys. We just need to, set up a little polarization experiment, and the results are identical. You can use one to figure out the other. But I didn't have this or nice polarizers ready to get a demo. So here we go. What I'm going to show you is that if we start with something polarized here with all white, and that's right now I have all vertical polarization here. And if I just put on this other box up there, which is going to be the other polarizer, if I put it the same way, this is all of our light electrons coming through all white, so it doesn't really do much. And if I look at the black output over here, the second color sorting box, it's the same as turning my polarizer 90 degrees. So nothing comes out black. So this is our, if we remove this guy from the middle, you have exactly what you expect. You sort here, you have white, and you get all white out. Great. Everyone thought that was easy. We all had that figured out. This box got thrown in the center here, and it became sort of confusing because you thought, well, they were white. I'm going to put my box in the middle here. That's this guy, 45 degrees. And then if I throw this guy on the end again, the idea was, well, they were all white here. So maybe this guy identified the soft ones from the light ones, and now we have white and soft because they still all be white, right? So I put this guy on up here. They should all come out, but sort of don't. And you say, well, are they black? Well, they're not really black either.
Whoa.
It's a combination of the two. Right, so that's this experiment done in polarizers. But let me just play the polarizer trick real quick because it's fun. So this is if I say vertical polarization and how many of them come out horizontal. So here I'm saying white and how many of them come out black. That's the analogy. Right, the answer is none of them. And strangely, if I take this thing, which seems to just attenuate, this is our middle box here, and I just stuff it in between them, I can get something to come out.
So this, like, I don't know. I don't know how you guys feel watching this, but this is crazy. Like, if you've seen these polarizers, it's kind of some 3D glasses use this polarizer technology, and they're kind of like sunglasses. It just makes things darker. So the idea that you'd have 2 of these and you could slide one in between, and you can clearly see in the middle there, like in the middle of this part, it's lighter, I mean, people ask me what my motivation to learn this is. Is this not crazy? Is this not like just an insane thing about the world that it works this way? Anyways, brief digression aside.
Even though I still have cross polarizers on the side. So you can see the middle region is now brighter. You can still see the dark corners there, the cross polarizers. As I turn this guy around, I can make that better or worse. The maximum is somewhere right there, and it goes off again. So this is a way of understanding our electron sorting hyper-intelligent monkeys in terms of polarizations. And here's just a vector projected on another vector, projected on another vector, something everybody knows how to do. So here's the polarization analogy of the Stan-Garlic experiment.
All right. Awesome. So the polarization analogy for interference effects in quantum mechanics is a canonical one in the text of quantum mechanics. So you'll find lots of books talking about this. It's a very useful analogy, and I encourage you to read more about it. We won't talk about it a whole lot more, but it's a useful one. All right, before we get going, any questions from last lecture? Last lecture was pretty much self-contained. It was experimental results. Yeah, nothing? All right. The one thing that I want to add to the last lecture, so one last experimental observation, I glossed over something that's kind of important, which is the following. So we started off by saying, look, we know that if I have a ray of light, it's a wave, it's an electromagnetic wave, and it has some wavelength lambda. And yet the photoelectric effect tells us that in addition to having the wavelength lambda, the energy, it has a frequency as well, a frequency time, and the photoelectric effect suggested that the energy is proportional to the frequency. And we wrote this as h nu, and h bar is equal to h upon 2 pi, and omega is equal to 2 pi nu. Okay, so this is just the angular frequency rather than the number per time frequency, and h bar is the reduced Planck constant. So I'll typically write h bar omega rather than h nu because these 2 pi's will just cause us endless pain if we don't use the bar. Anyway, so to a electromagnetic wave, that wavelength and frequency, and the photoelectric effect let us predict that the energy is linearly proportional to the frequency, with linear proportionality coefficient, h bar, Planck's constant, and the momentum is equal to h upon lambda. Whoops, h upon lambda, also known as, same right says h bar k, which is equal to h upon lambda. Where here again, h bar is h upon 2 pi, and so k is equal to 2 pi upon lambda.
K is wave number, and just what he's doing with the 2 pi's, he's turning it into radians per second rather than periods per second.
And a wavelength, or a wave number inverse wavelength. And the claim of the photoelectric effect is that the energy and the momentum of that light are thus quantized. The light comes in chunks. So it has a wave-like aspect. It also has properties that are more familiar for particles. Now, early on, shortly after Einstein proposed this, a young French physicist named de Broglie said, well, look, okay, this is true of light. Light has both wave-like and particle-like properties. Why is it just light? The world would be much more parsimonious if this relation were true not just of light, but also of all particles. I am thus conjecturing, with no evidence whatsoever, that in fact this relation holds not just for light, but for any object. Any object with momentum p has associated to a wavelength or a wave number, which is p upon h bar. Every object that has energy has associated with it a wave with frequency omega. To those electrons that we send through the Davis-Germer experiment apparatus, which are sent in with definite energy, there must be a frequency associated with it, omega, and a wavelength, lambda, associated with it. And what we saw from the Davis-Germer experiment was experimental confirmation of that prediction, that electrons have both particulate and wave-like features simultaneously. So these relations are called the de Broglie relations, or de Broglie. I leave it up to you to decide how to pronounce that.
I've been saying it on de Broglie.
And those relations are going to play an important role for us in the next few lectures. I just want to give them a name and a little context. This is a good example of parsimony and elegance, the theoretical elegance, leading you to an idea that turns out to be true of the world. Now, that's a dangerous strategy for finding truth, right? Boy, wouldn't it be nice if, right? Wouldn't it be nice if, we didn't have to pay taxes, but we also had Medicare. But of course, so it's not a terribly useful guide all the time, but sometimes it really does lead you in the right direction. This is a great example of physical intuition, widely divorced from experiment, pushing you in the right direction. I'm making it sound a little more shocking than, well, it was shocking. It was just shocking. Okay, so with that said, let me introduce the moves for the next few lectures. For the next several lectures, here's what we're going to do. I'm not going to give you experimental motivation. I give you experimental motivation. I'm going to give you a set of rules, okay? A set of postulates. These are going to be the rules of quantum mechanics. And what quantum mechanics is for us is a set of rules to allow us to make predictions about the world, okay? And these rules will be awesome if their predictions are good. And if their predictions are bad, these rules will suck, right? We will avoid bad rules to the degree possible and give you what we've learned over the past, 100 years. Wow, of developing quantum mechanics. That is amazing. Wow, okay, yeah, over the past 100 years of developing quantum mechanics. And I'm going to give them to you as a series of postulates, and then we're going to work through the consequences, and then we're going to spend the rest of the semester studying examples to develop an understanding for what the rules of quantum mechanics are getting you. Okay? So we're just going to scrap classical mechanics and start over from scratch. So let me do that. And to begin, let me start with the definition of a system. And to understand that definition, I want to start with classical mechanics as a guide. So in classical mechanics, let's think about the easiest classical system you can, just a single particle sitting somewhere. In classical mechanics of a single particle, how do you specify the configuration or the state, just different words for the same thing, how do you specify the configuration or state of the system? Specify the position momentum, exactly. So in classical mechanics, if you want to completely specify the configuration system, all you have to do is give me x and p for my particle, and if you tell me this, I know everything. If you know these numbers, you know everything. In particular, what I mean by saying you know everything is that if there's anything else you want to measure, the energy, for example, the energy is just a function of the position and momentum. And if you know the position and momentum, you can unambiguously calculate the energy. Similarly, the angular momentum, which is a vector, you can calculate if you know x and p, which is just, are across me. Okay? So this gives you complete knowledge of the system. There's nothing more to know if you know that data. Now, there are certainly still questions that you can't answer given knowledge of x and p. Okay? For example, are there 14 invisible monkeys standing behind me? I'm here, I'm not moving. Are there 14 invisible monkeys standing behind me? You can't answer that. It's a stupid question, right? Okay, let me give you another example. The electron is x and p, some position. Is it happy? Right? So there are still questions you can't answer. The point is complete knowledge of the system to answer any physically observable question, any question that can be meaningfully turned into an experiment. The answer is contained in knowing the state of the system. Cool? Okay. But this can't possibly be true in quantum mechanics because, as you saw in the problem set and as we discussed previously, there's an uncertainty relation, which says that your knowledge, or your uncertainty rather, in the position of a particle quantum mechanically. I'm not even say quantum mechanically, I'm going to say the real world. Okay. So in the real world, our uncertainty in the position of our point-like object and our uncertainty in the momentum is always greater than or roughly equal to something that's proportional to the Planck's constant. Okay. You can't be arbitrarily confident of the position and of the momentum simultaneously. You worked through a good example of this on the problem set. We saw this in the two-slit experiment and the interference of electrons. This is something we're going to have to deal with. So as a consequence, you can't possibly specify the position and the momentum with confidence of the system. You can't do it. Okay? This was a myth. It was a good approximation. Turned out to be false. So the first thing we need is to specify the state, the configuration of the system. So what specifies the configuration of the system? And so this brings us to the first postulate. The configuration or state of a system. And here, again, just for simplicity, I'm going to talk about a single object, of a quantum object. Is completely specified. Completely specified by a single function, a wave function, which I will denote generally psi of x, which is a complex function. Okay. The state of a quantum object is completely specified once you know the wave function of the system, which is a function of position. I'm going to absolutely emphasize that this is a first pass at the posits. What we're going to do is go through the basic posits of quantum mechanics, then we'll go through them again and give them a little more generality, and then we'll go through them again and give them full generality. That last pass is 805. Okay? So let me give you some examples. Let me just draw some characteristic wave functions. These are going to turn out to be useful for us. Yeah, good. So for example, consider the following function. So here's 0, and we're plotting it as a function of x, and I'm plotting the real part of psi of x. Okay. So first consider a very narrowly supported function. It's basically 0 everywhere, except it has some particular on it, what I'll call x1. Okay. Here's another wave function, 0. It's basically 0, except for some special spot at x2. Okay, and again, I'm plotting the real part of psi. And I'm plotting the real part of psi because A, psi is a complex function. At every point, it specifies a complex number. And B, I can't draw complex numbers. So to keep my head from exploding, I'm just plotting the real part of the wave function. So you should never forget that the wave function is complex. So for the moment, I'm going to assume that the imaginary part is 0. I'm just going to draw the real parts. So let me draw a couple more examples. What else could be a good wave function? Well, those are fine. What about, again, we want a function of x. I'm going to draw the real part. Okay. And another one. So this is going to be a perfectly good wave function. Okay. And we draw two more. So what else could be a reasonable wave function? Well, this is harder than you'd think. Okay. So that could be the wave function. I don't know. That is actually my signature. My wife called it a little gift. Okay, so here's the deal. Psi is a complex function. Psi also needs to not be a stupid function. Okay, so you have to ask me, look, could it be any function, any arbitrary function? So this is going to be a job for us. We're going to have to define what it means to be a not stupid function. Well, this is a completely reasonable function. It's fine. This is a reasonable function. Another reasonable function, reasonable. That's a little weird, but it's it's not horrible. That's stupid, right? That is a stupid. So we're going to have to come up with a good definition of what not stupid means. So fine, these are all functions. One of them is multi-valued, and that was a little worrying, but they're all functions. So here's the problem. What does it mean? So postulate 2. The meaning of the wave function is that the probability that upon measurement, the object is found at the position x is equal to the norm squared of psi of x. Okay. If you know the system is described by the wave function psi, and you want to look at point x and where with what probability will I find the particle there, the answer is psi squared. Notice that this is a complex number, but absolute value squared or norm squared in complex number is always a real non-negative number, and that's important because we want our probabilities to be real non-negative numbers. Could be 0, right? Could be 0 chance. So it can't be -7 chance. Okay. Incidentally, there also can't be probability 2, right? So that means that the total probability had better be normalized. So let me just say this in words though first. So P, which is the norm squared of psi, determines the probability, and it's the probability density, that the object in state psi, in the state given by the wave function psi of x, will be found at x. Okay. So there's the second postulate. So in particular, when I say it's a probability density, what I mean is the probability that it is found between the position x and x plus dx is equal to p of x dx. Okay. Which is equal to psi of x squared dx. Okay. Does that make sense? So the probability that is found in this infinitesimal interval is equal to this density times dx, or psi squared dx. Now again, we need, it's crucial that the wave function is in fact properly normalized, because if I say, look, something could either be here or it could be here, what's the sum of the probability that's here plus the probability that's here? And it better be 1, right? Or there's some other possibility. So probabilities have to sum the total probability that you find something somewhere must be 1. So what that tells you is that total probability is the integral over all possible values of x. So if I said over all possible values of x, p of x, all values should be equal to 1. And we can write this as integral dx over all values of x. And I write all here rather than putting minus infinity to infinity, because some systems will be defined from 1 to -1, some systems will be defined from minus infinity to infinity. All just means integrate over all possible values. Hold on one sec. Of psi squared. Yep. I'm not going to. Probability density is going to have just one argument, and total probability is going to be have an interval as an argument. Okay. So they're distinct, and this is just a notation. Other questions? Okay. Just as a side note, what are the dimensions of the wave function? Does everyone think about this one for a second?
Okay. What are the dimensions of the wave function? Ooh, I am not sure. Do we have information that would help us know here? Well, we know that it's going to be a probability density. I want to say dimensionless, but let's just see. This is my guess. All right, let's see what he says.
All right, what are dimensions? Awesome. Yes, it's 1 over length.
Oh.
Psi are 1 over length.
Nope.
And the way to see that is that this should equal 1. It's a total probability. This is an infinitesimal length, so this has dimensions of length. This has
right.
This must have dimensions of 1 over length.
Yeah.
So psi itself of x.
So it's because of this. All right. Yeah. And that's why I need to start writing down more of the math here, or I'm going to get lost. Dx is equal to 1. Ergo, it's going to be 1 over root length Okay.
Must have dimensions of whatever length. Now, something I want to emphasize, I'm going to emphasize over and over in this class, is dimensional analysis. You need to become comfortable with dimensional analysis. It's absolutely essential. Okay, it's essential for two reasons. First off, it's essential because I'm going to be merciless in taking off points if you do write down a dimensionally false thing. If you write down something on a problem set and it's like a length is equal to a velocity, ooh, not good. But the second thing is, forget the fact that I'm going to take off points. Dimensional analysis is an incredibly powerful tool for you. You can check something that you just calculated, and even better yet, sometimes you can just avoid a calculation entirely by doing dimensional analysis and seeing that there's only one possible way to build something of dimensions length in your system. So we'll do that over and over again. But this is a question I want you guys to start asking yourselves at every step along the way of the calculation. What are the dimensions of all the objects in my system? This smells like smoke. Okay, so with that said, if that's the meaning of the wave function, what physically can we take away? What physically can we take away from knowing these wave functions? Well, if this is the wave function, let's draw a probability distribution. What's the probability distribution? P of x. And the probability distribution here is really very simple. It's, again, 0 squared is still 0. So it's still just a big spike at x1. And this one is a big spike at x2. Okay. Everyone got that? So what do you know when I tell you that this is the wave function describing your system? You know that with great confidence, you will find the particle be sitting at x1 if you look. Right? So what this is telling you is you expect x is roughly x1, and our uncertainty in x is small. Everyone got that? Similarly here, you see that the position is likely to be x2, and your uncertainty in your measurement, or your confidence in your prediction, as another way to say, is quite good, so your uncertainty is small. And what about these guys? Well, now, it's norm squared. I need to tell you what the wave function is. Here's the wave function that I want. So here's 0. The wave function is e to the I k1x. And here, the wave function is equal to e to the I k2x. And remember, I'm drawing the real part because, of practical limitations. So the real part is just a sinusoid, or in fact, a cosine. And similarly here, the real part is a cosine. And I really should put 0 in the appropriate place. That worked out well. Okay, good. So now the question is, what's the probability distribution? P of x associated to these wave functions. So what's the norm squared of minus e to the I kx?
So let's do just a quick check to see if I remember, because this is something that came up in the problem sets that I wasn't sure how to do. Norm square, I think you have to multiply it by the complex conjugate, but I couldn't remember whether if you look at the unit circle, and this is imaginary and this is real. I think the complex conjugate was here, but like it's real plus imaginary, and then the complex conjugate is real minus imaginary. I believe this is the conjugate. So this is like y equals this, and then y star is equal to that, I think. So let's just try to do this problem, see if we can anticipate the result he's having here. So we have this e to the I k1x. So we know that this is equal to cosine of, I think this is cosine of k1x plus I sine of k1x. I believe that's the right formula. Again, this has been 8 years since I've done this. And again, I'm just working through this problem ahead of time just because I want to see whether I know it, or whether if he's just showing it, it's like, oh yeah, that is the right way to do it. So if we were to do the probability, we would need to get this. So this is going to be equal to the cosine of k1x plus I sine of k1x. And then this is going to be times cosine of k1x minus I sine k1x. So we have equals cos squared k1x. And I believe that it's this times this. So we've got negative sign and plus sign, so these should cancel. And then it's negative I, so this should be plus sine squared k1x. And I think cos squared plus sine squared, if we remember our identities from trigonometry, I think this is just equal to 1. So our probability should just be like this. I think. All right, I'm going to be embarrassed if this is not right, but embarrassment is part of learning, so let's figure it out.
If I have a complex number, phase e to the I alpha, and I take its norm squared, what do I get? 1, right? So remember complex numbers. If we have a complex number alpha, if we have a complex number beta, then beta squared is by definition beta complex conjugate times beta. So e to the I alpha, if the complex conjugate is e to the minus I alpha, e to the I alpha times e to the minus I alpha, they cancel out, that's 1. Okay?
So you did it rather faster than me, but same result, I think.
Well, it's 1. It's independent of x. So from this, we've learned 2 important things. The first is this is not properly normalized. That's not so key. But the most important thing is, if this is our wave function, and we subsequently measure the position of the particle, we look at it and say, there's the particle. Where are we likely to find it? It could be anywhere. Right? So what's the value of x you expect? Typical x. I have no idea. No information whatsoever. None. But, and correspondingly, what is our uncertainty in the position of x that we'll measure? It's very large. Exactly. Now, in order to tell you it's actually infinite, I need to stress this up and tell you that it's actually constant off infinity, and my arms aren't that long, so I'll just say large. Similarly here, if our wave function is e to the k2x, here k2 is larger, the wavelength is shorter. What's the probability distribution? It's again constant. Right? So it's 0, 0. So again, x, we have no idea. And our uncertainty in x is large. And in fact, it's very large. Everyone that? Questions? What about these guys? Okay, this is the real challenge. Okay, so if this is our wave function, and let's just say that it's real, hard as it is to believe that, then what's our probability distribution? Well, something like, I don't know, it's something, you get the point. Okay, so so if this is our probability distribution, where are we likely to find the particle? Well, now it's a little more difficult, right? Because we're unlikely to find it here. It's reasonably likely to find it here, unlikely here, reasonably likely, unlikely, it's a mess. So where is this? I'm not really sure. What's our uncertainty? Well, our uncertainty is not infinite, right? Because, okay, my name ends at some point, so this is going to go to 0. So whatever else we know it's in this region. So it's it's not infinite. It's not small. We'll say. But it's not arbitrarily. It's not tiny. Or sorry, it's not gigantic. That's what I meant. It's not. Our uncertainty is not gigantic. Not gigantic. But it's still pretty untrivial because I can say with some confidence it's more likely to be here than here, but I really don't know which of those peaks is going to be found. Okay. Now what about this guy? What's the probability distribution? Well, now you see why this is a stupid wave function. Because it's multiply valued. It has multiple different values at every value of x. So what's the probability? Well, it might be it's root 2, maybe it's 1 root 3. I'm really not sure. Right? So this tells us an important lesson. This is stupid. And what I mean by stupid is it is multiply valued. So the wave function, we just learned a lesson, should be single valued. Okay? And we will explore some more on your problem set, which will be posted immediately after lecture. There are problems that walk you through a variety of other potential pathologies of the wave function. And guide you to some more intuition. For example, the wave function really.
Yeah, we looked at that one, so I think we'll cover that in the problem set.
Questions at this point? Okay, so
Get all dark
these
in
look like
here.
pretty useful wave functions because they correspond to the particle being at some definite spot, and I, for example, at a reasonably definite spot. These 2 wave functions look pretty much useless because they give us no information whatsoever about what the position is. Everyone agree with that? Except, remember the de Broglie relations. The de Broglie relations say that associated to a particle is also some wave. And the momentum of that particle is determined by the wavelength. It's inversely related to the wavelength, proportional to the wave number. And the energy is proportional to the frequency. Now, look at those wave functions. Those wave functions give us no position information whatsoever, but they have very definite wavelengths. Those are periodic functions with definite wavelengths. In particular, this guy has a wavelength of from here to here. Yeah? It has a wave number k, k1. So that tells us that if we measure the momentum of this particle, we can be pretty confident because it has a reasonably well-defined wavelength corresponding to some wave number k, 2 pi upon the wavelength. It has some momentum, and if we measure it, we should be pretty confident the momentum will be h bar k1. Can you agree with that? Looks like a sine wave. And de Broglie tells us that if you have a wave with wavelength lambda, that corresponds to a particle having momentum p. Now, how confident can we be in that estimation of momentum? Well, if I tell you it's e to the kx, that's exactly a periodic function with wavelength lambda, 2 pi upon k. So how confident are we? Pretty confident. So our uncertainty in the position, or in the momentum, is tiny. Would you agree? Similarly, for this wave, again, we have a wavelength, it's a periodic function, but the wavelength is much shorter. If the wavelength is much shorter, then k is much larger, the momentum is much larger, so the momentum we expect to measure, which is roughly h bar k2, is going to be much larger. What about our uncertainty? Again, it's a perfect periodic function, so our uncertainty in the momentum is small. Ever go with that? And that comes, again, from the de Broglie relations. So, good. So questions at this point. Here's the real fight today. All right. Questions? Yeah.
So delta P is 0 basically?
It's pretty small. Now again, I can't runs off to infinity, but if it's exactly the IKX, then yeah, it turns out to be 0. Now, an important thing, so let me rephrase your question slightly. So the question was, is delta P 0? Is it really 0? So here's the problem for us right now, we don't have a definition of delta P. Right? So what is the definition of delta P? I haven't given you one. So here, when I said delta P is small, what I mean is, intuitively, just by eyeball, our confidence in that momentum is pretty good. Using the Fourier relations. I have not given you a definition, and that will be part of my job over the next couple of lectures. Very good question. Yeah?
So like how would you encode noise in that function? You just have different wavelengths.
Yes.
As you go along.
Awesome. So for example, this, does it have different wavelength? Not so much. So hold that question and wait till you see the next examples that I put on this board. And if that doesn't answer your question, ask it again because it's a very important question. Okay.
So when you talk about like a photon, that's like even, well, you always say like a photon has a certain frequency. Doesn't that mean that it must be a wave because you have to like fix the wave number k?
Awesome question. Does every wave packet of light that hits your eye, does it always have a single unique frequency? No, you can take multiple frequency sources and superpose them. An interesting choice of words, I guess, there. Right, so the question is, since light has a wavelength, does every chunk of light have a definite? This is the question. Yeah. So, and the answer is light doesn't always have a single. But you can have light coming at you that has many different wavelengths and put it in a prism and break it up into its various components. Right. So you can have a superposition of different frequencies of light. We'll see the same effect happening for us. Okay. So again, de Broglie made these. There we go. De Broglie made this conjecture that E is H bar omega, P is H bar K. This was verified in the Dixon-Gerber experiments that we ran. But here, one of the things that's sort of latent in this is what he means is, look, associated to every particle with energy E momentum P is a plane wave of the form e to the I kx minus omega t. Okay, this properly in 3 dimensions should be k dot x. But at this point, this is an important simplification. For the rest of 804, we are going to be doing one-dimensional, or for the rest of 804 until otherwise specified, we are going to be doing one-dimensional quantum mechanics. So I'm going to remove arrow marks and dot products. There's going to be one spatial dimension and one time dimension. We're always going to have just one time dimension, but sometimes we'll have more spatial dimension. But it's going to be a while until we get there. So for now, we're just going to have k to kx. So this is a general plane wave. And what de Broglie really was saying is that somehow associated to the particle with energy E and momentum P should be some wave, a plane wave, with wave number k and frequency omega, and that's the wave function associated to it. The thing is, not every wave function is a plane wave. Some wave functions are well localized. Some of them are just complicated morasses. And some of them are just a mess. Okay. So now is the most important postulate in quantum mechanics. I remember vividly when I took the analytical class. It was called Physics 143A at Harvard, and the professor at this point said, I know him well enough as a friend. He said, "This is what quantum mechanics is all about." And I was so psyched, and he told me, and it was like, "That's ridiculous. Seriously, that's what quantum mechanics is all about?" So I always thought like this is some weird thing where like old physicists go crazy, but it turns out I'm going to say exactly the same thing. This is the most important thing in all of quantum mechanics. It is all contained in the following proposition: everything. The two-slit experiments, the box experiments, all the cool stuff in quantum mechanics, all the strange and counterintuitive stuff comes directly from the next postulate. So here it is.
Which postulate are we on? 3?
3. Let's start on it. Given 2 possible wave functions or states, I'll say configurations of a quantum system. Which is like right of the Valkyries, like the background too. Of a quantum system corresponding to 2 distinct wave functions. Okay, F with an upper and S is going to be my notation for functions, because I have to write it a lot. Psi 1 and psi 2. I'll say of x. The system can also be in a superposition of psi 1 and psi 2. Where alpha and beta are complex numbers. Given any 2 possible configurations of the system, there is also an allowed configuration of the system corresponding to being in an arbitrary superposition of them. If an electron can be hard and it can be soft, it can also be in an arbitrary superposition of being hard and soft. And what I mean by that is that hard corresponds to some particular wave function. Soft will correspond to some particular wave function. And the superposition corresponds to a different wave function, which is a linear combination of them. Yeah, okay, that's a very good question. So A and B, alpha and beta are some complex numbers subject to the normalization condition. So indeed, this wave function should be properly normalized at the end. Now, let me step back for a second. There's an alternate way to phrase the probability distribution here, which goes like this. I'm going to put it here. The alternate statement of the probability distribution is that the probability density at x is equal to psi of x norm squared divided by the integral over all x dx of psi squared.
Nope, let me just get this written down. X squared.
Notice that if we properly normalize the wave function, this denominator is equal to 1.
Normalization.
But if we haven't properly normalized it, so it's not there, right? Then it's equivalent. But if we haven't properly normalized it, then this probability distribution is automatically properly normalized. Because this is a constant, when we integrate the top, that's equal to the bottom, it integrates to 1. Cool? So I prefer, personally, in thinking about this for the first pass, to just require that we always be careful to choose some normalization. That won't always be easy. And so sometimes it's useful to forget about normalizing and just define the probability distribution that way. Is that cool? Okay. This is the beating soul of quantum mechanics. Everything in quantum mechanics is forced on us from these few principles and a couple of currents of matching to reality. Yeah. Yes.
Can you get like interference?
Yes. So the question is, when you have a sum of two wave functions, can you get some sort of interference effect? The answer is absolutely, and that's exactly what we're going to do next. So in particular, let me look at a particular pair of superpositions. So let's swap these boards around. Parallelism is a little obvious. Okay. So let's scrap these rather silly wave functions and come up with something that's a little more interesting. So instead of using those as characteristic wave functions, I want to build superpositions. So in particular, I want to start by taking an arbitrary, both these wave functions are simple representation. This corresponds to a particle being here. This corresponds to a particle being here. I want to take a superposition of them. So here's my superposition. Okay. Oops. Try that again. Good. And my superposition, so here's 0, and here's x1, and here's x2. My superposition is going to be some amount times the first one, plus some amount times the second one. There's a superposition. Similarly, I could have taken a superposition of the two functions on the second chalkboard. And again, I'm taking a superposition of the complex EDIK1x and EDIK2x, and then taking the real part. Okay. So that's a particular superposition, particular linear combination. So now let's go back to this. This was a particle that was here. This was a particle that was there. When we take the superposition, what is the probability distribution? Where is this particle? Well, there's some amplitude that it's here, and there's some amplitude that it's here. There's rather more amplitude that's over here. There's still some probability that it's over here, right? Where am I going to find the particle? I'm not so sure anymore. It's either going to be here or here, but I'm not positive. It's more likely to be here than it is to be here, but not a whole lot more. So where am I going to find the particle? Well, now we have to define this, where I'm going to find the particle. Look, if I did this experiment a whole bunch of times, it'd be over here more than it would be over here. So the average will be somewhere around here. It'll be in between the two. So x is somewhere in between. That's where we expect to find it. On average. Okay. What's our uncertainty in the position? Well, it's not that small anymore. It's now, of order x1 minus x2. Everybody agree with that? Bless you. Now, what about this guy? Well, does this thing have a period? Does it have a single wavelength? Sorry? No. This is like light that comes at you from the sun. It has many wavelengths. In this case, it has just two. I've added those together. So this is a plane wave, which is psi, is EDIK1x plus EDIK2x. Okay. So in fact, it has two wavelengths associated with it. Lambda 1 and lambda 2. And so the probability distribution now, if we take the norm squared of this, the probability distribution now, which is the norm squared of this guy, is no longer constant, but there's an interference term. And let's just see how that works out. Let me be very explicit about this. Note that the probability in our superposition of psi 1 plus psi 2, which I'll call EDIK1x plus EDIK2x, the probability is equal to the norm squared of the wave function, which is the superposition psi 1 plus beta psi 2, which is equal to alpha squared psi 1 squared plus beta squared psi 2 squared plus alpha star psi 1 star, actually let me write this over here, plus alpha star psi 1 star beta psi 2 beta star psi 2 star, where star means complex conjugation. But notice that this is equal to that first term is alpha squared times the first probability, or the probability of this thing of alpha psi 1. This is equal to probability 1. This term, beta squared psi 2 squared, is the probability that the second thing happens. But these terms can't be understood in terms of the probabilities of psi 1. Under probability of psi 2 alone, they're interference terms.
Just put a,
So
just
the
gonna put a
superposition
marker
principle,
here.
together with the
48, 50.
interpretation of the probability as the norm squared of the wave function, gives us a correction to the classical addition of probabilities, which is these interference terms. Everyone happy with that? And here's something very important to keep in mind. These things are norm squares of complex numbers. That means they're real, but they're non-negative. So these two are both real and non-negative. But what about this? This is not the norm squared of anything. However, this is a complex conjugate. When you take something that's complex conjugate and add them together, you get something that's necessarily real, but it's not necessarily positive. So this is a funny thing. The probability that something happens if we add together two configurations, we superimpose two configurations, has a positive probability term, but it's also got terms that don't have a definite sign. That could be negative. It's always real. And you can check that this quantity is always greater than or equal to 0. It's never negative, the total quantity. So remember Bell's inequality that we talked about? Bell's inequality said, look, the probability of one thing happening, if we have the probability of one thing happening being P1 and the probability of the other thing happening being P2, the probability of both things happening is just P1 plus P2. And here we see that in quantum mechanics, probabilities don't add that way. The wave functions add, and the probability is the norm squared of the wave function. The wave functions add, not the probabilities. And that is what underlies all of the interference effects we see. And it's going to be the heart of the rest of quantum mechanics. So you're probably all going in your head, or else like I was when I took Peter Quantum, like, yeah, but I mean, it's just, you're adding complex numbers. But trust me on this one. This is where it's all starting. Okay, so let's go back to this. Similarly, let's look at this example. We've taken the norm squared, and now we have an interference effect. Now our probability distribution, instead of being totally trivial and containing no information, our probability distribution now contains some information about the position of the object. It's likely to be here. It is unlikely to be here. Likely and unlikely. We now have some position information. We don't have enough to say where it is, but X is we have some information. Okay. Now our uncertainty is still gigantic. Delta X is still huge. You know, but okay, we just added together two plane waves. Yeah.
Big, small, big, small.
Excellent. This was the real part of the wave function, right? And the wave function is a complex quantity. When you take e to the ik1, let me do this on the chalkboard. When you take e to the ik1x plus e to the ik2x, let me write this like differently. E to the ia plus e to the ib, and take its norm squared. Okay. So this is equal to. I'm going to write this in a slightly more suggestive way. The norm squared of e to the ia times 1 plus e to the I b minus a. Okay. Norm squared. Oops. Parentheses. Norm squared. So first off, the norm squared of a product of things is the product of the norm squareds. So I can do that. And this overall phase, the norm squared of a phase is just 1. So that's just 1. So now we have the norm squared of 1 plus a complex number. Okay. And so this is the norm squared of 1 is going to give me 1. The norm squared of the complex number is going to give me 1. And the cross terms are going to give me the real part, twice the real part, of e to the ib minus a, which is going to be equal to cosine of b minus a. Okay. And so what you see here is you have a single frequency in the superposition. Cool. Okay. So again, here, so good. So our uncertainty is large. So let's look at the second example in a little more detail. By superposing two states with wavelength lambda 1 and lambda 2, or k1 and k2. Wow. With wavelength lambda 1 and lambda 2, we get something that's okay. It's still not well localized. We don't know where the particle is going to be, but it's better localized than it was before, right? What happens if we superpose with 3 wavelengths, or 4, or more? So for that, I want to pull out a mathematical package. You guys should all have seen Fourier analysis in. You should all have seen Fourier analysis in 1803, but just in case, I'm putting on the web page, on the Stellar page, a notebook that walks you through the basics of Fourier analysis in Mathematica. You should all be fluent in Mathematica. If you're not, you should probably come up to speed on it. That's not what we wanted. Let's try that again. There we go. Oh, that's awesome. Or by awesome, I mean not. It's coming. Okay, good. Okay, I'm not going to mess with the screens after last time. So I'm not going to go through the details of this package, but what this does is walk you through the superposition of wave packs. So here, I'm looking at the probability distribution coming from summing up a bunch of plane waves with some definite frequency. So here it's just 1. Okay, that's 1 wave. So first we have. Let me make this bigger. Yes, stupid mathematical tricks. So here we have the wave function, and here we have the probability distribution, the norm squared. Okay. Okay, and it's sort of badly normalized here. So that's for a single wave, and as you see, the probability distribution is constant. And that's not 0, that's 0.15. It's just I arbitrarily normalize this. So let's add 2 plane waves. And now what you see is the same effect as we had here. You see a slightly more localized wave function. Now you have a little bit of structure in the probability distribution. So there's the structure of the probability distribution. We have a little more information about where the particle is. More likely to be here than it is to be here. Let's add one more. And as we keep adding more and more plane waves to our superposition, the wave function and the probability distribution associated with it become more and more well localized. Yeah? Until as we go to very high numbers of plane waves that we're superposing, we get an extremely narrow probability distribution, and wave function for that matter. Extremely narrow, corresponding to a particle that's very likely to be here and unlikely to be anywhere else. Remember that? What's the expense? What have we lost in the process? Well, we know with great confidence now that the particle will be found here upon observation. But what will its momentum be? Yeah, now it's a superposition of a whole bunch of different momenta. So if it's a superposition of a whole bunch of different momenta, that's here, this is like superposition of a whole bunch of different positions, right? Likely to be here, likely to be here, likely to be here, likely to be here. What's our knowledge of its position is not very good. Similarly, now that we have superposed many different momenta with comparable strength, in fact, here they were all with unit strength, we now have no information about what the momentum is anymore. It could be anything in that superposition. So now we're seeing quite sharply the uncertainty relation. And here it is. Back to so the uncertainty relation is now pretty clear from these guys. Oops, that didn't work. Good. So the uncertainty relation is, and I'm going to leave it alone, this is enough for the Fourier analysis, but that Fourier package is available with extensive commentary on the Starling pitch. Yeah.
Now, is that sharp definition in position caused by the interference between all those waves and all that?
That's exactly what it is. Precisely the interference between the different momentum nodes that leads to certainty in the position. That's exactly right. Yeah. Exactly. Here we are. So in this example, we have no idea what the position is. We're quite confident of the momentum. Here we have no idea what the position is, but we have great confidence in the momentum. So here we have less perfect confidence in the position, and here we have less perfect confidence in the momentum. It would be nice to be able to estimate what our uncertainty is in the momentum here and what our uncertainty is in the position here. So we're going to have to do that. That's going to be one of our next tasks. Other questions? Yeah.
This is kind of the part
Yeah.
where you said obviously the question has a lot more in S2 than S1.
Yes.
The average. So what is going to be in that?
Yeah, that's right. So because it's a probability distribution, it won't be exactly at that point, but it'll be nearby. Okay, so in order to be more precise, and so for example, for this, here's a quick question. How well do you know the position of this particle? Pretty well, right? But how well do you know its momentum? Well, so we don't like to see how very, but tell me why. Why is your uncertainty in the momentum of the particle large? Yeah, but that's a cheat because we haven't actually proved Heisenberg's uncertainty principle. It's just something we're inheriting. I believe it too, but I want a better argument because I believe all sorts of crazy stuff. So I really do. So black holes, fluids. I mean, don't get me started. Yeah. Yeah, excellent. Okay, we'll get to that in just one second. So before taking a Fourier transform, which is an excellent. The answer was just take a Fourier transform. We're gonna do that in just a moment. But before we do Fourier transform, just intuitively, why would De Broglie look at this and say, no, that doesn't have a definite momentum? Yeah, there's no wavelength, right? It's not periodic by any stretch of the imagination. It doesn't look like a thing with a definite wavelength. And De Broglie said, look, if you have a definite wavelength, then you have a definite momentum. And if you have a definite momentum, you have a definite wavelength. This is not a wave with a definite wavelength, so it is not corresponding to the wave function for a particle with a definite momentum. So our momentum is unknown, so this is large. And similarly here, our uncertainty in the momentum is large. Okay? So to do better than this, we need to introduce the Fourier transform. And I want to do that now. So you've all seen, you should all have seen Fourier series in 803. Now we're going to use the Fourier transform, and I'm going to introduce this to you in 804 conventions in the following way. And the theorem says the following. I'm not going to prove it by any stretch of imagination, but the theorem says any function f(x) that is sufficiently well behaved, it shouldn't be discontinuous, it shouldn't be singular, any reasonably well behaved non-stupid function f(x) can be built like enough plane waves of the form e to the ikx. Enough may be infinite. So f(x), any function f(x) can be expressed as 1 over root 2 pi. And this root 2 pi is a choice of normalization. Everyone has their own conventions, and these are the ones we'll be using to go throughout. Minus infinity to infinity. And k, f tilde of k, e to the ikx. So here what we're doing is we're summing over plane waves of the form e to the ikx. These are modes with a definite wavelength, 2 pi upon k. F tilde of k is telling us the amplitude of the wave with wavelength lambda or wave number k. And we sum over all possible values. And the claim is any function can be expressed as a superposition of plane waves in this form. Cool? And this is for functions which are non-periodic on a real line rather than periodic functions on the interval, which is what you should have seen in 803. Now, conveniently, if you know f tilde of k, you can compute f of x by doing the sum. But suppose you know f of x and you want to determine what the coefficients are, the expansion coefficients. That's the inverse Fourier transform. And the statement for that is that f tilde of k is equal to 1 over root 2 pi integral from minus infinity to infinity dx f of x e to the minus I kx. And that's sometimes referred to as the inverse Fourier transform. Okay. And here's something absolutely essential. F tilde of k, the Fourier transform coefficient of f of x, are completely equivalent. If you know f of x, you can determine f tilde of k. And if you know f tilde of k, you can determine f of x by just doing the sum, by just adding them up. Okay. So now here's the physical version of this. Oh, I can't slide that up. The physical version of this, I'm now going to put here.
I think I'm just going to go back a little bit.
So the physical version. Slide
Write down this formula.
F of x, you can determine f tilde.
Yeah, dx.
Okay.
This is me not remembering my formulas. F of x e to the negative.
You can determine f of x by just doing the sum, by just adding them up.
E to the negative I chi x. Okay.
So now here's the physical version of this. Oh, I can't slide that up. The physical version of this, I'm now going to put here. So no, I'm not going to put that down here. So the physical version of this is that any wave function. Good. Any wave function, side eyes, can be expressed as a superposition in the form psi of x is equal to 1 over root 2 pi integral from minus infinity to infinity dk psi tilde of k e to the I kx. Oops. Of states or wave functions with a definite momentum. P is equal to h bar k. And so now, it's useful to sketch the Fourier transforms of each of these functions. So in fact, I want this up here. So there is research. So here we have the function and its probability distribution. Now I want to draw the Fourier transforms of these guys. So here's psi tilde of k, function of a different variable than of x, but nonetheless it's illuminating to draw them next to each other. And again, I'm drawing the real part. And here, x2, had I had my brothers about me, I would have put x2 a larger value. Good. Just further off to the right there. And similarly, I'm so loath to erase the superposition principle. Unfortunately, I'm not there yet. Let's look at the Fourier transform of these guys. So the Fourier transform of this guy is now, oops, this is k, psi tilde of k. Well, that's something with a definite value of k. And its Fourier transform is 0. There's k1. And for this guy, 0. K2. And now if we look at the Fourier transforms of these guys, this way I don't have to erase the superposition principle. The Fourier transforms of these guys and the Fourier transform of this guy. So note that there's a sort of pleasing symmetry here. If your wave function is well localized, corresponding to your Fourier transform is not well localized, corresponding to not having a definite momentum. On the other hand, if you have definite momentum, Your position is not well defined, but the Fourier transform has a single peak. The Fourier transform has a single peak at the value of k corresponding to the momentum of your wave function. Remember that? So here's the question. Sorry, there's a raised hand.
How are we going to learn in this class how to determine Fourier transforms of these non-zero functions?
Yes, that'll be your homework. On your homework is an extensive list of functions for you to compute Fourier transforms of, and that will be the job of process recitation. So Fourier series and computing, yeah, you know what I'm talking about. So Fourier series are assumed to have been covered for everyone in 803 and 1803, and something you're probably should know. And Fourier transforms, good help. So Fourier transforms are slightly indicating the space of Fourier series because knowledge of your functions, yeah.
So we're doing a Fourier transform of Wavefunction. Basically, writing as a continuous set of different waves. Can you write as a discrete set of the Fourier series?
Absolutely. So, however, what is true about Fourier series? When you use a discrete set of momentum, it must be periodic function, exactly. So the question is, do you always have to secure times we said, look, we're writing a wave function, or arbitrary wave function, as a continuous superposition, continuous value of possible momentum. This is absolutely correct. That's exactly what we're doing. However, that kind of annoying. This continuous, we need to one method, two method, three method. We're doing a discrete series. So discrete is fine. But if you make that discrete series interrelated to each other, so when you do a Fourier series, you force the function at best to be periodic. And we don't want that in general, because life isn't periodic. Thank goodness, right? I mean, there's like one film in which it, but so, it's a good movie. So that's the essential difference between Fourier series and Fourier transforms. Fourier transforms are continuous in K and do not assume periodicity of the function. Other questions? Yeah.
Basically, the Fourier transform associates the amplitude and phase for each of the individual.
Precisely correct. So let me say that again. So the question was, so a Fourier transform effectively associates a magnitude and a phase for each possible wave vector. And that's exactly right. So here, there's some amplitude and phase. This is a complex number because this is a complex function. There's some complex number which is an amplitude and a phase associated to every possible momentum going into the superposition. That amplitude may be zero. There may be no contribution for a large number of momentum, or maybe insignificantly small. But it is indeed doing precisely that. It's associated with amplitude and phase for every plane wave, with every value momentum. And you can compute before panicking. You can compute precisely what that amplitude and phase is by using the inverse Fourier transform. Right. So there's no magic here. You just calculate. You can use your calculator. Literally. Hate that word. Okay, so now here's a natural question. So if this is the Fourier transform of our wave function, this wave function, we already knew that this wave function corresponded to having a definite from de Broglie. We know that it has a definite momentum, right? We also see that its Fourier transform looks like this. So that leads to a reasonable guess. What do you think the probability distribution, P of k, is probability density? The probability density to find the momentum to have wave vector k, h bar k. Yeah, that's a pretty reasonable guess. So here's just, we're totally pulling this out of the dark, psi of k norm squared. Okay, well, let's see if that works. So psi of k norm squared for this is going to give us nice, well-localized function. Similarly, psi of k for this guy. So that makes a lot of sense. It's exactly what we expected, right? Definite value of p with very small uncertainty. Similarly here, definite value of p with very small uncertainty. Rock on. However, let's look at this guy. What is the expected value of p if this is the Fourier transform? Well, remember, we have to take the norm squared, and psi of k was e to the I kx1. The Fourier transform, you will do much practice on 15 Fourier transforms on the problem set. Where did my eraser go? There it is. Farewell, principle 1. So what does norm squared of psi still look like? Well, just like before, the norm squared is constant, because the norm squared of the phase is constant. And again, the norm squared, this is psi tilde of k norm squared. So we believe, or conjecturing, this is p of k. You will prove this relation on your problem set. You'll prove that it falls from what we said before. And similarly, this is constant, e to the I kx2. Okay. So now we have no knowledge of the momentum. So that also fits. The momentum is we have no idea, and uncertainty is large. And the momentum is we have no idea, and the uncertainty is large. So in all of these cases, we see that we satisfy quite nicely the uncertainty relation: small position momentum, large momentum uncertainty. Large position uncertainty, we're allowed to have small momentum uncertainty. And here, it's a little more complicated. We have a little bit of knowledge of position, and we have a little bit of knowledge of momentum. We have a little bit of knowledge of position, and we have a little bit of knowledge of momentum. So we'll walk through examples with superposition like this on the problem set. Okay. Last question before we get going. Okay, so I have two things to do before we're done. The first is, after lecture ends, I have clickers, and anyone who wants to borrow clickers, you're welcome to come down and pick them up in a first come, first served basis. I will start using the clickers in the next lecture. So if you don't already have them, get one now. But the second thing is, don't get started yet. I have a demo to do. And last time I told you, this is awesome. It's like having experimental for a day. Last time I told you that one of the experimental facts of life is One of the experimental facts of life. One of the experimental facts of life is that there is uncertainty in the world. And that there is probability, that there are unlikely events that happen with some probability, some finite probability. And a good example of the randomness of the real world involves radiation. So hopefully you can hear this. Apparently, I'm not very radioactive. You'd be surprised at the things that are radioactive. Yep, got a little tick. Shh. Okay. This is a plate sold at an Amish county fair. It's called Vaseline ware, and it's made of local clays. It's got uranium in it. Okay? But even more exciting, I want to emphasize, exactly when something goes click. It sounds pretty random, and it's actually a better random number generator than anything you'll find in, Mathematica or C. In fact, for some purposes, the decay of radioactive isotopes is used as the perfect random number generator, because it really is totally random as far as anyone can tell. But here's my favorite. People used to eat off these. See you next time.
All right, so we have finished lecture 3. Let me just switch back to note view here. So I'm going to be wrapping up today. I've got about another 20 minutes for this studying session. So let's do what I've been doing the whole time. Let's spend like 5 minutes recapping what was discussed in this lecture. So there were three postulates, or 3 kind of like main principles of quantum mechanics. So one of them was that you could represent everything in a wave function. The other one was that the superposition principle, basically if you get 2 different wave functions, you can add them together, and that's also a valid wave function. Don't remember what number 2 was. This is partially the problem with free recalls. You sometimes don't remember everything, but it's good to just kind of stretch your brain a little bit. So usually it'll be something obvious that I'm skipping over because I don't code the memory that way. What is number 2? The meaning, of course. So this is it. So the meaning of the wave function is that if you take the norm squared of that, then you will get the probability of finding whatever particle we're considering with this wave function in that location, or the probability density function is the norm squared of this. So there's some interesting stuff from here. One of it was a big discussion in the Fourier transform. I was under the impression that the Fourier transform was covered in 1803. I seem to remember taking it in 1803, but I did in the MIT challenge some classes that went beyond that, in particular signals and systems. Did a lot of stuff. Electrical engineering does a lot of stuff with the Fourier transform. So for me, the Fourier transform is like one of the most baked in concepts from the MIT challenge, even though I don't use it very much today, just because that idea of switching between position domain, frequency domain. I mean, I don't do the calculus that much, but the conceptual understanding is pretty pinned down. So you notice I wasn't taking that many notes in that section because it was fairly obvious to me. Some things that weren't as obvious to me. So you'll note that I wrote down some questions here. So one of the things here is I put a note for the timestamp. So whenever there's something I don't write down the full formula, for instance, because it's going too fast or there's a lot of algebra, I like to put little timestamps just in case I'm going through my notes and I'm like, okay, this is important. I want to go back and check it. I know when this happened in the lecture. I don't do it too often, but I do it occasionally. And one of the things that came up here for me, which I didn't get the clear answer in the lecture, but I feel like he said that the implication is that the probability density can be negative for like the value of px can be less than 0 for some x, which seems wrong to me. But this idea was just that the interference terms is going to be a real value, but it might be negative. Now, maybe what he meant by that was that this sum in for any particular x is going to be between, 0 and 1 or something. So p of x, for all x, p of x is going to be in the intervals between 0 and 1. However, these interference terms might be negative. So this is something that I'm a little bit unclear of right now. So I'm going to be looking at that's sort of one of the things that I have to kind of evaluate a little bit. So I'll take just a second right now just to pause to answer some questions. And if I have a few minutes left, maybe now is a good time to play around with some of these formulas, see if I can answer this important question that came up. Were there any other questions that came up? Well, I've got to get better at doing my complex exponentials. I went through the big process of breaking this apart into cosines and sines and multiplying it to get, this trigonomic identity of 1, whereas he was just like, oh, we know this is 1. So I'm taking a little bit longer here. So this is going to show that my math is going to be maybe a little bit more shaky. Similarly, this right here, this plane wave, which has like an X spread and a time spread. So there's like this is also something that I kind of remember, but is getting a little shaky. So if this is getting in the math, we might have to take space, separate ourselves out, learn some of these concepts, master some of the math, and then come back. So I got asked by someone whether I'm going to be making these notes online. I don't think I'm going to do it right now, but I'm hoping, partially it's just because I don't want to rip things out of this spiral notebook until I'm done the class. But when I'm done, I think what I might do is scan everything. I do have a scanner here, so I might go through and just scan everything in one big document or in a bunch of documents at the end. They tend to be kind of large files, which is unfortunate, but I'll try to get these notes later eventually. My hope in doing this is just you can kind of see how I'm taking notes, how I'm kind of going through it. So we do have about 10 minutes left. I mean, I kind of started a little early, so maybe I don't necessarily want to go through a full set of practice right now because it's kind of getting low on time. Maybe I'll just go through a little bit some of the comments that were made, just respond to a few things real quickly here. So on second thought, the channel says, recommends the Barton Zwiebak lectures. I didn't watch that class, but I've seen him as a guest lecturer. He comes in for 1 or 2 guest lectures on this one, and I liked Alan Adams a lot more as a lecturer. Maybe he's just more entertaining. But I will keep that in mind because maybe Zwiebak is a bit better on the math, and if that's what I'm struggling with, maybe I should go to those lectures. So I will just take a look at some of these things now. So I got a few minutes left. Often when I end the day like this, you know, this is a good point. I don't really want to start a new lecture yet. I've already done kind of a little bit of a recap of what I've learned so far. I want to kind of just take stock of what we've learned. So I went through the problem set, and now we've done 3 of the lectures. Now we haven't gotten up to the point where the problem sets were linked. I don't remember exactly where that was, where the problem sets were, or problem set 4 was supposed to be due. I think it was like lecture 8 or something. So we haven't hit the point where we've covered all the material that we covered in our brief scan of the problem sets. But if I have to look at it, I think, yeah, definitely going to have to get more comfortable with some of my complex math. I feel like, again, I learned these things, but I learned it like 8 years ago. So I'm going to have to do a little bit of practice on that. Definitely like complex conjugate, making sure I'm getting my complex exponentials right, doing this sort of functional stuff. I think so far there hasn't been a ton of math done. I noticed I made a mistake guessing the dimensional analysis. So that was right here. I guessed that the dimensions of the wave function were dimensionless, and it was not. It was 1 over L. But I guess that also makes sense because when you think about it, what is the probability? This is 1 over L squared. So if you square this is 1 over L, and what is the probability density function? It's, you know, an amount of probability per length. But that's something I keep track of too. I think the dimensional analysis, making sure I'm working with the units, is something that I'm going to have to work on. So I don't think I've seen enough of the class yet to get a real feel for what's going to be difficult going forward, but I'm going to go forward tomorrow. I think at this rate I did, what did I do? I did about 2.5 classes this afternoon, and I did about half the class this morning. So, you know, if that rate holds, I might be able to get 5 classes done tomorrow. And then if I had only 2 more to do on the on Wednesday, then we could get started with the problem sets a little earlier. And that's always good because if you can get started with the problem sets. So I don't know whether there's that much more to do right now. I'm going to make just some notes of some of the things. So I like to do just sort of a little end of day analysis. I used to do this in my day summary. I used to just write these sort of little mini journals after each day in the MIT Challenge notes, and they're just good for taking stock of what you've done. So what did I do? I covered sort of the, you know, pre-class P-sets, and I did kind of go from 1 to 4, although not in as much depth for number 4. And I watched lectures 1 to lecture 3. I feel like if we're going to cover the content, what are some of the things we learned here? Well, we learned about some quantum oddities, some sort of strange facts about quantum physics, namely that you can just basically these sort of mysteries about why, you know, it's very unusual and strange. That was sort of lecture 1. Lecture 2, we talked about certain facts of life, some facts of physics, and those in particular we're talking about. There's atoms, there's atomic spectra, which are discrete. So we're talking about photoelectric effect, which is that energy, so Ke is proportional to the frequency of photons, well, I should say of light, ergo photons. What else did we do? We did diffraction, including single emission, so one photon at a time, one electron at a time. What was the other thing? Bell's inequality, which is what you'd expect, but QM violates this. And this sort of implies that what the quantum stated is somewhat more complicated. And then what do we have? Also there was randomness, but I think randomness was kind of also covered in here. And then what did we talk about in the third lecture? Well, there was 3 principles. One of them was the wave function. This is the sort of representation of the particle. We had number 2. Ooh, what's number 2 again? Oh, right. The norm squared is equal to the probability density. And number 3 is basically this. We can have x is equal to alpha psi 1 x plus beta psi 2 x, and then this is so this is interpretation, and then this is superposition. So I think I feel pretty good about how we covered things today. I'll just leave this up of this kind of what we covered today. I feel pretty good about it so far. I mean, we haven't gotten any super hard math. I think from looking at the problem set, some of the math is going to be like just kind of refresher math that I'm a little bit like this radiative collapse, the atoms on these classical calculations. They're not from this class. We didn't cover it here. They're from, you know, either 8 years ago or a class I didn't take. So I'm thinking there might be a little bit of hiccups doing problem set 1. That's maybe going to be the hardest problem set because it's going to lean more heavily on stuff that I haven't actually covered immediately. But I feel pretty good about what's going on here in terms of intuition. I mean, we're still pretty early on, but already we have this kind of intuition about the uncertainty relation, which is that, you know, if we can describe things in terms of wave functions, then when we look at wave functions, it's natural to have this uncertainty relation because it just falls out just automatically from the fact that something that has a very definite position has a very distributed frequency space, and something that has a very distributed frequency space has a more defined momentum. And so this is this uncertainty relation, which is very obvious. So this is the kind of thing that I'm trying to go up for and why we're getting into math, because if you didn't understand how the Fourier transform worked, it would be a lot harder to understand why it is the case that something that has a very definite momentum has a less defined position, and vice versa. Like, and I think that there's still a lot of mysteries that we haven't resolved yet. They've just been introduced. So again, one of the main ones is that, you know, how, like, well, you guys saw if you were watching, if you guys saw it at the beginning of the last lecture of lecture 3, how they did this thing with the polarizers. And I mean, it's kind of mind blowing. Like polarizers are like this kind of stuff that you have in some types of sunglass lens. And if you tilt them, if you tilt them at right angles and it polarizes this way and this one polarizes this way and you get them polarized this way, it will block all the light. And it's just crazy that if you insert one at this angle in between, it lets more light through. Like that's, it doesn't make sense, but it makes sense in this kind of thing. And so we haven't gotten to an explanation yet that I think would be really satisfactory for understanding this. But, we've kind of laid out the mysteries, what's at stake. And no, this is really interesting. I'm going to be back tomorrow, same time. I'm going to try to do 8 to 11 and then 2 till 5. And I'm just going to keep doing this for all of April. And yeah, well, we'll see how it goes. And thank you guys for watching. I know some of you are hanging out and watching me while I'm doing this. And for some of you, you may be watching this long after it's recorded and long after today, in which case, yeah, thanks for watching. And I will wish me luck for tomorrow.